Okay, good morning, everyone here in the room and remotely at home in the offices. Welcome so much for attending the third and last edition of Sol2H2O Fast Track School. I must say that this initiative has been rather successful in our projects. So we have had in all of the editions very interesting number of attendants, both on site and remotely. And we can also have a good token of the quality of the materials we have been presenting in these editions by the fact that we have had already around 900 downloads of these materials in our Zenodo repository. So this is, I guess, a very good token that what we are trying to provide to the research community, to industry partners, is of value and is raising interest. So I thank you for your interest, and this is exactly the objective of So as most of you already know, especially those which have already attended previous editions of this fast track school, we are organizing this initiative in the scope of Sol2H2O, a project funded by the European Commission through Horizon Europe. And the objective of this project is to steer the research activities in wider countries such as Portugal, also mainly through cooperation with partners from non-wide countries, and in this case, we have the pleasure to be collaborating with NIPA, EC, and CMARS in Spain. Definitely, this to us, the University of Évora, has been an excellent endeavor because it has enabled us not only to strengthen the cooperation that we already had with these institutions, but also to strengthen a new research line in our research group around water production and water treatment technologies based driven by solar energy. And of course, it is our expectation that what we are trying to do in the projects will live beyond the projects and will be also of use in Portugal. As we are now starting to have more focus on desalination technologies, with the construction of the first desalination plants in Portugal mainland. So Portugal actually has a desalination plant since the 80s in a small island on the archipelago of Madeira. Can you hear me at home?
Now better, but not so good.
Okay, I will try to speak louder.
Thank you.
Okay. Well, anyway, I was just making a brief introduction to what are these fast track school editions and what is Sol2H2O. And without further ado, I would like to thank you again for attending, to welcome you to this third edition, and hoping that it will be successful as the previous editions have been, especially in terms of your interests and of the contribution to your research groups. Thank you so much. Okay, I think it's working.
Good morning, everyone. Hope you are enjoying the Fast Track School for now. I will do a brief presentation regarding the overview of the installer capacity on desalination. So this is a brief introduction for what will pass during the day on this Fast Track School. So here I will show more or less, most of you already know this, but I will show actual recent data that is reported from 2022-2023. So here on the first slide, I have explanation about the seawater and the brackish water, as you can see on the right side, is the main feed for the desalination plants in nowadays. So on the left side, you have seawater, and in brackish water, you can see from 2003 until 2023, how was the contracted capacity regarding the feed water type. And we can see that seawater is the mainly used for the desalination. So here we can say that we have more or less two main technologies, membrane technology and thermal technology. So from the chart on the right side, you can see that membrane technology is the most used and the most common technology that is being used on the desalination process. So, and regarding the chart that we have a division, how it can be considered a technology for membrane part and thermal part, we can see the reverse osmosis is the mainly used technology, and the thermal part is most of that divided by multi-state flushing technology and multi-effect distillation technology. So from this, we can say that reverse osmosis and multi-state flush technology, most of the multi-state flush is being used in Middle East countries, are currently dominated the global market. So I have a brief note that on Europe, regarding Europe, we can say that 88.5% of the technology is used nowadays is reverse osmosis. And as I said previously, MENA region countries, countries that are north of Africa and Middle East countries, they use most of the 31% of the technology being used is multi-state flush, and 9% is the technology being used is multi-effect distillation. So here it is reported on 2022 that more or less they exist 21,000 desalination plants active. So, and the global production of these 21,000 plants are 99 million cubic meters per day. So here on this chart, we can see on orange the installed capacity by year from 2003 until 2023, and on the bars, the blue bars, it shows the cumulative contracted new desalination plants. So, as I said previously, here we can see how is distributed the desalination regarding over the globe. So, Middle East and North of Africa, they represent altogether 70% of the global capacity in desalination. And regarding Europe, the data shows that only 10% is the number of representation in the global capacity. In this chart, we can see that we have some common countries, that is Asia, that they are getting some acquirements on the desalination, and America and Europe is represented on the rest of the world. That is the white blue color, like so. So, and here I can show a top 10 by installed capacity. This is reported from 2024. The top 10 countries and the installed capacity in million cubic meters per day. And we can see that the first European country that appears is Spain, that is positioned on the 5th position, and the rest of them is Middle East, China and United States that are getting growing their capacity on desalination. Most of them is small desalination plants regarding China that are being used to support small village for agriculture water. So in here regarding Europe, it's just a simple overview about the capacity, how it is distributed, and the capacity on Europe. We can see on the map that most of the countries are located on the Mediterranean regions. That's where are most of the desalination plants. There is important that they exist 2,336 desalinating plants installed in Europe, but only 1,779 are active facilities nowadays, that they use seawater and brackish water. They can supply 7.92 million cubic meters per day. And this is how usually is distributed this water that is produced by desalination, that can be for most of them public water supply, industrial applications, power plants, and irrigation. So here I want to show how it is the installed capacity growing from 2003 until 2023. And we are seeing from here, from this chart, that plants that produce more than 500 cubic meters per day are getting more grow, and they are being used more recently regarding Middle East countries, that they are increasing their capacity on desalination. Here I have a list of the 20 countries and 20 power desalination plants that have been awarded from 2002 until 2023. So what you can see in more darker color, this is new desalination plants, that is new contracts regarding 2022 and 2023. And the other ones is power plants that are being increasing their capacity, and they are changing the membranes or changing the technology. So as you can see, regarding the orange color, most of them are seawater reverse osmosis technology, and you can see they're still going some constructions regarding multi-stage flush and multi-effect distillation. The pink color represents the multi-stage flush, and the darker pink color represents the MET technology. So here, as you can see, capacity already is been increasing. So here we have 1 million cubic meters per day of capacity on this desalination plant, more regarding Saudi Arabia and UAE.
Iba a escribir, el coche ha sobrevivido. ¿Ya ha ido a la torre?
Lo he visto de arriba.
¿Has visto?
Okay.
Nos tenían vigilados.
So, about production costs, I want to show here what is the information that we get nowadays. So, regarding the size of the plants, so we have from above 100 cubic meters per day, we have production costs that can be from 1.2 euros per cubic meter until 15 euros per cubic meter. So, plants regarding 50,000 and 60,000 capacity, more or less the costs are 38 cents until €1.30. And here we have these values for plants that are more or less from 100,000 cubic meters until 320,000 cubic meters. The costs are really much lower. So what I could understood from here, and what I get the information, this is regarding Middle East countries. So they have fees and they have support from the state to get the tariffs low. So that's why these costs are presented here, and they do not represent the reality from the other countries, let's say that. And here I want to show for the three main technologies, multi-stage METs and reverse osmosis, how could be the total energy consumption per cubic meter regarding these technologies. As we can see, for reverse osmosis, we can go from 3 until 5.5 kilowatt hour per cubic meter. So, and we don't have thermal energy needed. So, because multi-state flushing meant they need thermal energy. So here, that's why reverse osmosis from the beginning of my presentation is getting interest and is getting higher implementations. And that's it. If all the reference that I have shown, they are here present, and just a small overview of the desalination capacity is implemented. Okay, thank you. This one? No. Yo creo que esto o esta. Yo creo esta.
So good morning, everyone, the people here and attendants from online. My name is Juan Antonio La Fuente. I work as a grades engineer at the ITC Water Department. Today we're having 8 presentations, apart from the one made by Federico. 4 of them will be focused on the benchmarking of the different technologies, and the other 4 will be focused on the exploitation contents and market opportunities, and will be offered by different companies. Well, I will start with a brief introduction of why shall we use PV designation. Just one slide trying to answer that question. I will continue by giving an overview of the key performance indicators that are used for the comparison of this benchmarking and the final solutions that we can find in the market. After that, we will see the products on the market and the successful experiences. We'll have the opportunity to hear the chief engineer from Solar Water Solutions that will explain the product on the market. After that, we will see the challenges and the future opportunities found, and I will finalize with some conclusions. Well, why PV designation, PV power designation? Well, PV power designation is considered the most promising forms of renewable energy power among all the existing possibilities. The first PV designation plan on a commercial scale was investigated in 1981 in Saudi Arabia. Since then, numerous studies have focused on using solar PV for driving reverse osmosis desalination plants on a small scale. As you can see in the graph, PV is the most widespread combination. Almost 1/3 of all the autonomous desalination systems are based on this combination. How can we answer the question why PV? Possibly saying that both solar PV energy and reverse osmosis desalination are mature technologies that come on with a wide commercial network of manufacturers and suppliers. There's a large market opportunity for solar powered aero desalination technologies, mainly in areas with good solar resource and brackish of water, or seawater for desalination. But a challenge to realize these market opportunities face off with the variable nature of solar resource. For a desalination plant, this variability in the solar resource can lead to high water cost due to mainly to low capacity factors and increased maintenance costs, mainly due to startups and shutdowns of the plant. Now we will see the KPIs. PV benchmarking refers mainly to the process of evaluating and comparing the performance efficiency and effectiveness of PV desalination systems. This will involve assessing the key performance indicators, such as there are many, but the main ones are the water recovery rate, specific energy consumption, the CAPEX, OPEX, and the levelized cost of water. Comparing them across different system designs, manufacturers, and operational conditions. Which is the purpose, the main purpose of doing this UÉvora benchmarking? Well, we can find just to identify the best performing technologies for different feed water scientists and operation conditions. Also to optimize UÉvora system designs for energy savings and cost reductions. Why not to compare performance across different climatic conditions around the world? And of course, to guide investment decisions in sustainable destination projects. The benchmarking approach we have done for UÉvora is mainly based on comparative analysis. The first way to do it is to compare different UÉvora systems based on performance of these APIs. And the second way we will see different charts is by comparing case studies of existing desalination systems. For the first form, we find the most used key performance indicators. I have grouped them in categories. Dealing with energy efficiency, we find the specific energy consumption, the energy recovery efficiency, and the PV system performance ratio. On the side of water production and quality, we find the permit flow rate, the recovery rate, and the product water quality. Within the cost metrics, is a very important issue. We find the CAPEX, OPEX, and the levelized cost of water. Of course, the membrane replacement frequency and cost, but this could be included in the OPEX. And finally, the system reliability and sustainability. We find the downtime and maintenance requirements for isolated systems, the scalability and modularity, and the carbon footprint reduction. This is the first table where we can compare 3 different systems, UÉvora systems, based on the production scale. We find the small scale, the medium, and the large scale. The example applications for each system. For small scale, we find in villages and disaster relief areas. The medium scale, mainly located in coastal communities and for hotels. And the large scale, over 500 cubic meters per day, we find for industrial and municipal desalination. Dealing with the feed water type, the first systems are more used for brackish water desalination, although you can also find small-scale desalination systems for seawater desalination. With the medium scale, we find both brackish and seawater desalination, and for large scale, we find only seawater desalination UÉvora systems. Dealing with the solar activity capacity in the range of 5 to 50 kilowatt peak, 50 to 500 or 500 up to 10 megawatt in the large desalination systems. As for the energy recovery, no energy recovery devices are used commonly in brackish water small capacity systems. They are used for medium scale seawater RO desalination systems and high efficiency for the largest systems. The specific energy consumption we found is between 1.2 and 2.5 kilowatt hour per cubic meter in the first type of systems, between 2.5 and 4 in the medium scale, and between 3 to 4.5 in the large scale. I would like to highlight that at ITC, we have recently break the barrier of the 2 kilowatt hour per cubic meter for seawater desalination as a specific energy consumption. Well, the recovery rate between 40 to 65 in brackish water small scale desalination, from 40 to 50 medium scale, and large scale from 35 to 45. An important issue is the levelized cost of water. We can see clearly that always with this item, we found that we increase the capacity, the production capacity of the plant, we lower the levelized cost of water because of the economy of scale. The battery requirements, it's optional for small systems. You can direct couple them to solar energy. It's often required to medium scale systems, and of course, large battery or hybrid systems could be used with a grid backup in large scale. Autonomy of hours of operation, we found between 6 to 8 in the small scale, 8 to 12 in the medium scale, and up to 24 hours if you have the grid backup. And the maintenance complexity, we find low in the small capacity, production capacity destination plants, medium and high in the largest capacity. The second way of comparing different systems is by using existing case studies and comparing them. We have here 4 different systems. The first one will be deeply explained by Tommy Laninsalo. He's the chief engineer of Solar-Water Solutions that will give us a talk later on. It's a system, a small-scale off-grid system installed in Kenya, Kitui, with just 3 cubic meters per day production capacity. The second one is a grid-connected system installed in Abu Dhabi. There's a curious system floating PV row in Singapore and the large scale in Arabia Saudi in Neom. We can see the capacities, the PV capacities installed, the free water type. In the small scale, we find brackish water, seawater for the other 3, and the TDS, free water TDS, the recovery ratio, the specific energy consumption, we find 2.8 because we don't use any recovery. 4.5. This is high specific energy consumption because the free water TDS is also high. 3.9 in Singapore and 3.7 in Neom. Dealing with the levelized cost of water, we find again that as we go down in the production capacity, the levelized cost of water is higher. And the system type is the first case study is off-grid and modular design. The case in Abu Dhabi is a grid backup hybrid system. The one in Singapore floating PV row, and the large system is fixed in Saudi Arabia. Some key takeaway messages from this comparison, this benchmarking. You can say that small-scale off-grid systems are feasible for remote locations. They are mainly modular systems with minimal maintenance required, like higher costs due to economic scale. The second case, highly grid-connected systems are more reliable, but depend on grid availability. In remote locations, many times you don't find electrical grid, and has slightly higher energy consumption due to the higher salinity of seawater in that place. The floating PV row solution can optimize space requirement and can achieve reasonable energy efficiency, but requires of robust anchoring and wave resistance system. And finally, the large-scale PV row plants achieve the lowest levelized cost of water due to economies of scale, but require significant initial investment, and of course are expensive in the land use, and they are suitable for long-term water security. Just to highlight that the levelized cost of water includes both CapEx and OpEx. Well, we will see now some products on the market. Just a few slides to give you an overview of the ITC background on this topic. We have a patent called the Sol that has been transferred to a Canary Islands company. We have actually 5 systems, different systems installed in Africa. The first one was commissioned in May 2006 in Sarginen, Tunisia, in the desert. It's all of the systems are brackish water desalination in inland locations. The other 4 systems were installed 2 years after that in different locations of Morocco, Amelou, Tangarfa, Tasekra, and Azla. And this is the last system we installed in Mayo, the island of Mayo, Ribeira Dom Joao, Évora. This is a seawater reverse osmosis desalination system. And what we did is to install a PV field and a battery bank as a backup system to an existing seawater reverse osmosis desalination plant that at that moment was fed by a diesel generator, which was maintained in case of emergency. And we just made a retrofit of the plant. It passed from 100 cubic meters per day of production capacity to 120 cubic meters per day. Well, this is the first of the companies that will present today the system. I will not go in much detail because we'll have a later presentation on that. Just to say that it's a company, Solar-Water Solutions, based in Finland. They have an innovative approach that enables the direct connection of solar without the needs of batteries, inverters, and so on. Here we have the system we saw, the case study we saw before in Italy, in Kenya, and this is for brackish water desalination. The second company is a French company called Osmosan. The technology could be installed fully off grid or connected to the grid. The production capacities go from the range to 1 cubic meter per day to 2,000 in the case of seawater aero desalination, and from 5 to 2,000 in the case of brackish water. In 1916, it was implemented the first Osmosan system within the Master Renewable Energy Desalination Program. This PV seawater resource osmosis desalination system worked without batteries, and at that time they achieved the lowest specific energy consumption with 2.5 kilowatt hour per cubic meter. Here you have the successful experiences of this system. More than 40 Osmosan systems operating in 20 countries. You can find in French Polynesia, Cape Verde, Mauritius, South Africa, Mozambique, Namibia, and Vanuatu. They are both for sea and brackish water desalination, the different production capacities, and the beneficiaries of those systems. Here we have the third company, it's Elemental Water Makers from the Netherlands. The water production capacities are between 3.8 to 100 cubic meters per day. They state that the cost of desalinated water for seawater desalination is between 1 to 2 euros per cubic meter, including in the investment, transportation, commissioning, training, because it's important to train local people to operate and maintain the installation, as well as the operational expenses for 15 years. Here you have the table with the different water production capacities, the solar energy needed, and the specific energy consumptions, and all the systems that have been installed. And finally, we have an Italian company, Genius Water, that works off-grid battery-less to power seawater and brackish water desalination systems. The production capacity goes from 20 to 3,000 cubic meters per day. They say that the whole system can run even with a low sunlight levels, less than 200 watts per square meter, and they operate 9 hours daily. The successful experience, just to highlight one of them, the system they installed in Boavista, in Cape Verde. It is a brackish water desalination system with 75 cubic meters per day of desalination capacity. Now we are going to focus on the challenges and the future opportunities that we can find for PVRO desalination. Well, I have divided those challenges into 2 groups: the technical challenges and the economical challenges. I have highlighted 6 for each group. The first one we find is the variable solar energy supply. The solar reliance fluctuations leads to unstable power supply to the RO operation, and the energy storage by batteries or hybrid system are often necessary, but this adds complexity and cost to the system. The second technical challenge will be the energy storage limitation. Of course, batteries increase the system the reliability, but have limited lifespans and require replacements. High cost, low energy efficiency, and degradation make these batteries integration a challenge within the system. Aero systems are efficiency and energy demand. Of course, aero is an energy intensive process. We need energy devices in order to lower that specific energy consumption, and optimizing the energy use while ensuring consistent water production is the major challenging design. The membrane fouling and maintenance during the operation of PVRO desalination system, we can find shutdown and startups of the plant more frequently than in normal operation. That can lead to frequent cleaning, increases operational downtime and maintenance costs. The system design and scalability. PVRO systems must be custom designed. It's an important thing in those systems. Based mainly on solar availability, the water demand, and the salinity levels. It's not the same to design brackish water or seawater desalination systems. And finally, it's an important issue also, the brine disposal and environmental impact. Aero systems, as you already know, they generate high salinity brine, which can harm local ecosystems if they are improperly discharged. But sustainable brine management strategies, such as mineral recovery or brine concentration, could be implemented, but they require additional infrastructure and costs. The second group of challenges are the economic challenges. You can find a high capital cost, I commented before. PBO designation has a high initial investment due to solar panels, high pressure pump, energy recovery devices, and so on, membranes. The total installed cost can range from 2,000 to 5,000 euros per kilowatt installed of this capacity, depending, of course, of the system size and the location. These prices are for the whole system, not only for the PV system, but also for the aero plant. An important issue is the levelized cost of water considerations. The target of 1.5 euro per cubic meter for this levelized cost of water is really challenging due to the energy costs and the maintenance and system depreciation. After that, the cost of energy storage and backup systems, as we commented, batteries significantly increase project costs, typically between 200 and 400 euros per cubic meter in the case of lithium-ion batteries. There are alternative energy storage systems, but they are not always feasible in remote areas where more systems we can find. And hybrid PV, wind, or PV diesel systems require additional investment and operational complexity. The limited access to financing and incentives is a very important issue. Many PV projects in developing regions struggle with the lack of incentives, subsidies, financial subsidies from the local governments. The private investment is limited because they perceive risks as long payback periods. We're talking about 5 to 10 years. And innovative financing models are needed in order to widespread this type of systems. The supply chain is and spare parts availability. This is very important when we work in remote locations. In these locations, often we find the lack of local suppliers for PV components, and importing those spare parts from abroad is could be very costly. Of course, we need skilled technicians for system maintenance. It's very important to train local people to operate and maintenance those systems. And finally, the operational and maintenance costs, regular member replacement, and maintenance, cleaning chemicals, and recurring expenses in those systems. The lack, as I told before, the lack of trained personnel, and the remote monitoring and automation can help, but they require additional investment in Internet of the Things and control system, more accurate control systems. Now we will face the future opportunities in the PBO sector. We find the technological advances, mainly in high efficiency solar panels, direct PBO coupling, advanced membrane technologies, hybrid energy integration, and of course, digitalization and smart monitoring. In the first stage, we find the emerging perovskite silicon tandem solar cells that they state efficiencies above 30%, reducing the land use and the panel requirements. We also find the bifacial solar panels that can capture reflected sunlight, increasing the energy yield. In the side of direct PV air coupling without batteries, we find that using variable speed high pressure pumps and energy recovery devices allows the direct coupling of PV to aero systems without the use of batteries. A smart control algorithm can adjust the system operation based on the solar availability, and reducing the battery reliance significantly lowers the capital and maintenance cost of the system. In the group of advanced membrane technologies, we find the graphene-based and carbon nanotube membranes of high permeability and anti-fouling properties. The biomimetic membranes inspired by aquaporins allow an energy-efficient water filtration. And also the self-cleaning membranes reduce fouling and extend the membrane lifespan. The hybrid energy integration, we find PV wind aero systems provide a more reliable energy mix by compensating that solar intermittency, and hydrogen-based storage could also serve as a future alternative to batteries, although it's difficult for remote locations. And finally, digitalization and smart monitoring, we find that Internet of the Things-based remote monitoring and artificial intelligence-driven predictive maintenance can enhance the system efficiency and reduce the downtime. And finally, the smart sensors can optimize water production based on the real-time solar availability and the demand, the water demand. More future opportunities, in this case, based on the economic and market expansion, the declining cost of PV and aero components, we find that solar PV modules costs continue to decline, making PV more cost competitive. Mass production of high-pressure pumps and eligible devices will further reduce system costs. We are always talking on the economies of scale. The larger plants have more different eligible devices, for example, than the small production capacity systems. The membrane improvements will also extend lifespan and lower replacement costs. In the side of modular and decentralized systems, we find containerized PVO solutions provide plug-and-play options for remote communities. The scalable microgrid integrated aero plants can serve for both households and industries. This is very important, the green financing and carbon credits, growing emphasis on the decarbonization and net zero goals creates funding opportunities for this kind of system, PVO projects. The carbon credits and water credits could provide additional revenue streams, and the public-private partnerships can enhance affordability and accessibility for these kind of systems. And finally, the water energy food nexus, PVO designation for agriculture can support food production in arid regions. Solar-powered greenhouses using designated water can boost the crop yields. And the integrated aquaponics and desalination could be a sustainable food production model for many areas. We are now finalizing sustainable environmental innovations. The brine management is very important. Take in mind that when we're talking on brackish water desalination in remote areas, they are mostly inland locations, so the brine management is an issue to take into account. The innovations in brine treatment, such as zero liquid discharge and mineral recovery, can reduce the environmental impact. Using brine for salt production, aquaculture, or other applications can also create an additional value. The climate adaptation and disaster resilience, solar-powered mobile desalination units can provide emergency water supply after a natural disaster. PVO can support drought-prone regions by offering climate-resilient water resources. And the policy and infrastructure developments. The government incentives and policy support is very important in those cases. Incentives such as feed-in tariffs for renewable desalination can accelerate the adoption of these type of systems. Policies encouraging water energy integration can attract investment. And the international aid and development funds can support off-grid PVO systems in water-scarce regions. And the expansion into emerging markets, we find maybe Africa, South Asia, and Middle East present a high demand for off-grid desalination solutions. The rural electrification programs could also integrate PVO for water security in those areas. And decentralized PVO plants can serve island nations and remote coastal communities. And just to finalize, here we can find a brief conclusion. We know that PV powered aero desalination is a mature and commercial implementation. The feasibility, both technical and economical, has been demonstrated since 1981. Different concepts has been demonstrated in a large number of case studies we have seen. The competitive solutions using this coupling for isolated and water-stressed places have been shown worldwide. Due to the modularity, this is an important thing of aero. This system can be adapted to the available energy with easy operation, although an accurate control system is required, of course. The PV panels cost reduction has motivated an acceleration of this type of implementations. PV row connected to the grid can be an excellent solution to industrial processes. We can get up to 35% in OPEX reduction. A challenge we find is the connection with isolated microgrids and the control of the energy loads. And going inside the messages, the key messages, takeaway messages, PV row design holds a great potential for sustainable and decentralized water production, particularly in remote areas. While we find challenges, of course, such as high initial costs, energy storage, and membrane fouling, remain advancements, as we can see, solar efficiency, membrane technology, and direct PV row coupling, and smart monitoring can drive down the cost and enhance the feasibility of the PV row systems. And finally, the sustainable brine management with modular designs and green financing will further enhance the competitiveness of this type of systems. I think that's all. Yeah.
I wonder, you have shown us a lot of numbers and costs for PVRO systems, and of course, the final costs and what production of a PVRO system depends on solar resource. So I haven't seen any information on the correlation between solar resource and final cost.
Yeah, we have just compared different systems operating, one in Kenya, another one in Saudi Arabia. I don't have that information, but of course the costs are very on-site dependent.
You have a rule of thumb of when is it more advantageous to have a PVRO system or the RO wind system in terms of solar resource, in terms of wind resource? Is there a rule of thumb for that?
I don't have that information, but of course, with a good solar resource, for example, in Izquierdo, we have both good wind resource and with good solar resource. And I think we have 3,000 equivalent hours of wind and more than 6 kilowatt of solar resource. And we have tested both, just with solar PV energy and hybrid system and just wind energy. And of course, you have a cost reduction in the water production cost with a hybrid system. I don't know all around the world which is the limit of the solar resource in which you change to or implement also wind energy.
Let's imagine you would have a similar resource, solar or wind. What would be the cheapest solution?
It depends on the production capacity. For perhaps for low production capacity, it's feasible, it's good PV. But if you go to the medium or large scale, you will go to wind energy. But of course, it will depend on the type of desalination practice of the water and on the site.
You have shown us a number of cost reduction prospects. Me personally, find that this very steep cost reduction on the site is kind of solved because of overcapacity and one of the factors. Batteries, on the other hand, the costs has been reducing for the last 5 years, also very significantly. But would you see any breakthrough on both the energy recovery devices, high pressure pumping?
In the site of the reverse osmosis system, the energy recovery devices have achieved an energy efficiency close to 98%. So there's not much scope left there for an improvement. In the site of membranes, yes, there.
In terms of the reduction of costs for the manufacturer.
Yeah, of course. When you see large desalination plants in Saudi Arabia and Middle East, with all this, thank you so much. in the economy of scale, when you find more possibility of different energy devices, high pressure pumps, than in the low reduction capacity systems, you find cost reductions there. Sure. But mainly in the membrane, aero membranes are now focused on reducing the energy consumption and the prices.
Tony, is there for grid connected Évora resources units, is there an optimal ratio between the installed capacity, water capacity, and the EV power capacity? Because I see
For grid connected.
yes.
For grid connected.
We can, because I see a big variation.
Yeah, in the case studies, you
in
mean.
Saudi Arabia, you have huge PV, relatively small.
No, but take in mind that the case of Saudi Arabia is grid connected, but the case in Kitui, Kenya, is off-grid system. And the first one is for brackish water desalination, and the other one is for seawater desalination.
Because what I have in mind is, if you have a reverse osmosis plant with a power consumption of, I don't know,
For off-grid operation, you must take in mind around 6 to 8 hours of operation. So if you want to have nominal production capacity, just take in mind that you won't operate those 24 hours, as in the case of
for grid connected. If you have a plant of
for grid connected,
100
example,
kilowatt power installed, it makes sense to make a PV plant of 100 kilowatt peak.
That's a good question. It makes sense. In Saudi Arabia, they can install huge PV installations. They put it in the grid and they consume many kilometers away that energy from the grid. That is not really renewable desalination.
Yes.
You know, you put energy onto the grid and you get it from the grid. In that cases, you can install or whatever you want, because not you compensate. You consume here and you inject here. But that is not the common use of renewable energy desalination. That's a way they make in Saudi Arabia, for example. Not only for PV, also for wind energies.
So there is no rule.
For them now.
Well, I guess the difference is when
Just trying to compensate the energy you get for reverse osmosis desalination, you compensate by producing it by PV or wind.
but at the end of the day, it's not a technical decision, it's an economic decision.
Your device is connected.
Right.
But the thing is, the reality, as Federico stated before, the reality in some parts of the world is totally different from Europe, for example. The desalination reality in Saudi Arabia is nothing to do with it. They go down with the levelized cost of water. We can't afford here in Europe those prices. Of course, because of the economic scale.
Sorry. I have one more question. When we look at these prices and we compare them with water prices coming from the public grid, of course, there is a cost which is hidden there, which is the infrastructure, the distribution infrastructure. And sometimes it's not easy to understand what is the cost due to infrastructure. Is there an idea on how distance from the water distribution grid you need to be for it to be economically feasible, the isolated?
I have that. I don't have the figure, but I have in mind one paper we did many years ago for off-grid desalination, PV or brackish water off-grid desalination. It's not how away are you from the electrical grid. The question is if you have flexibility. In the case, for example, the first the source system with study
In this case, I mean from the water distribution.
from the water, no. And you're talking about a compared grid design.
No,
Okay.
compared to have whatever, on mid or
Yeah.
mid desalination, we just having infrastructure to distribute water brought to them.
You used to have it near, for those cases, you have on grid designation. Yeah, the water deployment network is used to be, the problem is when you have remote locations, that makes a difference between getting your water from tankers once a week or getting your own resource on site. But for on-grid designation, you used to have the distribution network there, sure. So now we are having the presentation from Alba from Plataforma Solar de Almería, and she will explain the benchmarking on membrane distillation technology.
Thank you very much, Tony. ¿Es not updated? Sí, pero he puesto el PowerPoint a esto. A lo mejor no se ha actualizado. No. Es que entonces no se puede ver en presentación. No. No.
Yes, you have to open it. You are opening it from the right. You should download it and
Yes. Yes. Yes, but it's not updated. But it's not updated because I put. But I need to make that. This is the. Okay. Sorry. Porque no lo puedo abrir como presentación. Pues yo he subido en PowerPoint, pero no aparece. No sé. Bueno, so good morning everybody. Today I'm going to follow the same index than Juan Antonio, but focus on membrane distillation technology. The first question to answer is why to use solar thermal membrane distillation, and that is because membrane distillation is a thermal technology that has several.
sorry, but I don't think we cannot see almost half of the screen.
Okay.
And I'm not sure
we would be the people at home would be able to see that.
Pero yo subí el PowerPoint hace media hora.
What's the problem? You know what's the problem?
No. Is moment Sol2H2O?
Should be on boundary, right?
Yes. No.
Reason?
No. Yes, but I put it. Thank you. Okay. So membrane distillation is a thermal technology that can operate in a temperature range between 60 and 80. And this allows to couple this technology with a low enthalpy energy source like solar thermal energy or waste heat. This is a good characteristic because in general the regions that face with water stress effect is the regions with a highest availability of solar radiation. Another advantage of membrane insulation is that it's more tolerant to the stop-start cycle to adapt with the weather condition, with the availability of the solar radiation, and also the storage of solar energy is cheaper than other renewable energy source. Also, the membrane distillation is a good technology to use for the brine concentration because this technology is not limited by the osmotic pressure, so it can treat fish solution with a high concentration of salts, with concentration higher than 70 grams per liter. So it's a good technology to install in places, in island places without the problem of the brine disposal in this particular complex. Also, the membrane distillation is modular, so this is another characteristic that makes it more adaptable to a small scale application than other thermal technologies such as the multi-step distillation that are bigger and is less adaptable to the small scale application. The other things of membrane distillation is that the membrane used in these technologies are hydrophobic, and this is a good characteristic to obtain a very high quality of permeate, and also this membrane has a lower tendency to fouling and scaling, reducing the deterioration of this membrane when we use a high concentration of salts. So all of these characteristics make it very attractive to some specific application that I will explain later. Now I will move into the key performance indicator. and I'm going to focus on the energy efficiency at pilot scale and the evolution of this parameter throughout the years that membrane distillation started to be more attractive. The first things that was introduced in the design of the membrane distillation technology in order to decrease the specific thermal energy consumption to improve the energy efficiency in this technology was the path from the design of plate and frame to spiral wound design in order to introduce the internal heat recovery in this technology. We can see here different ND modules from different companies with a design of plate and frame configuration. We can see that the values of specific thermal energy consumption are very, very high, up to 2,600 kilowatts per hour per cubic meter. That is not, it's not possible to have for a real application of this technology. But however, when the internal heat recovery was introduced with the spiral wound design, this value reduced up to values more acceptable, that is 256 kilowatts per hour per cubic meter. So only the change of the design to plate and frame to a spiral wound for the recovery of the internal heat recovery decrease the specific thermal energy consumption in a high percentage. The other modification to try to increase the energy efficiency in this technology was the modification of the channel length in the different ND modules. The different channel length in the module vary the resident times of the fluid solution inside the channel. If we increase the length of the channel, we increase the internal heat recovery inside the module, increasing the energy efficiency. But on the contrary, we decrease the permeate flux that we obtain. Here we can see two different ND modules from the same company, from the Aqua Steel, that are totally the same. Only the difference is the length of the channel. Here as a 1.5 meter, and here the length of the channel is 5 meters. And we can see that the specific thermal energy consumption reduced until the middle, until the half, in the case of the longest length of the channel. The other modification in the design was to introduce the multi-envelope configuration in the channel. The difference is that each channel in the ND module, the permeate channel, the core channel, and the feed channel, is formed by several envelopes. This introduced that the production inside the production in the ND module with higher envelopes increase. So we have more production with the same heat input, and this decreases also the specific thermal energy consumption. Here we can see a comparison of two ND modules. This is with only one channel, and this is the other from Aqua Steel that has 6 channels. We can see with a very similar membrane surface area, the production was the double with the same specific thermal energy consumption. And the last improvement to increase the energy efficiency in the ND at a level of pilot scale was the extraction of the air of the non-condensed gases in the channel, in the permeate channel, in the air gap channel. This reduced the resistance of the mass transfer, considering the same heat power. For that, when we introduce this configuration, the vacuum air gap membrane distillation, the specific thermal energy consumption was reduced. We can see two different ND models with the two configuration. When we have the configuration of the aggregate membrane distillation, the specific thermal energy consumption was lower than when we introduce the vacuum membrane distillation. When we remove the air in the air pack, we can see that the specific thermal energy consumption was reduced. And in particular, this ND module with this configuration obtain the specific thermal energy consumption with a very, very, very acceptable value. For that, we can say that this module with 12 number of the channels, with the multi-envelope configuration, also with a length on the channel of 2.7, and with the introduction of the spiral one configuration, and also the introduction of the vacuum assisted in the configuration, obtain the minimum specific thermal energy consumption obtained up to now. Here we can see an overview of the different ND modules from different companies, and we can see the evolution of the specific thermal energy consumption from very high values to the lowest value reached from this company that is Aquasteel. This is the products that is currently in the market. That is the model from Aquasteel company that has the different improvement in order to increase the specific thermal energy consumption with a very acceptable also production of permit with a high quality of permit. And now we move on to the successful experience in the field of the membrane distillation system. First of all, the Plataforma Solar of Almería. We have already operate and characterize some model difference ND models. We currently operate and characterize most of the ND model existing in the market, and we operate in the Plataforma with a very under a relevant environment compared to the solar field. Here we can see another ND pilot plant that is in the facility of Sol that was developed under the AgroConnect project. That this system is composed of a reverse osmosis unit compared to a membrane distillation system in order to continue concentrating the reversion of the reverse osmosis with the membrane distillation. The membrane distillation system is compared to a solar field to supply the thermal energy, and also the reverse osmosis is connected to a photovoltaic solar field in order to obtain the electric energy needed. Both are the function of the system is to produce the water to supply the water in a greenhouse. Here there is another successful ND pilot plant installed in an island in Vietnam. This is a pilot plant from Aquasteel company, and the production of this system is 43 liters per hour of a high quality water with a specific thermal energy consumption of 87 kilowatts per hour per cubic meters. The cost of the water here is very high, but compared to the previous operation that was imported the water from another island, the cost was reduced from $50 per cubic meter to $20 per cubic meters. And the last pilot plant installed from Aquasteel is another ND pilot plant installed in the Bonaire in a resort, in the Barbidae resort. This pilot plant has the particularity that the energy is supplied by the waste heat from the Jensen's waste heat. the distillate flash was 2.6 liters per hour per square meter, and the quality of the distillate was of high quality production. Another successful experience, but not to produce the high quality water, was the demo that was developed under the project Reversen. In this particular application, the use of the membrane distillation was coupled with the reactive precipitation and also the diffusion dialysis in order to regeneration of the copper electroplating bath. Here, in the reactive precipitation was obtained copper that currently is sold by the half of the cost of the fresh raw material of copper. And now we move on to the challenge. I divided the challenge into three different challenges. The one is the energy efficiency, the other the permit production, and finally the quality of the permit. Regarding the thermal energy, although the specific thermal energy consumption has reduced in the last year, currently this value continues being very high. So we have to continue trying to introduce improvement to reduce this value. Here I show an example of a work that we calculated the levelized cost of water for a specific application of produce fresh water, a total production of 100 cubic meters per day. And we obtained that the levelized cost of water depending on the thermal energy cost. The orange line is related to this model, and we can see that if we increase the thermal energy cost, the levelized cost of water was high. Considering a value of the solar thermal energy of 0.036 euro per cubic meters and an electric energy cost of 0.07 euro per cubic meter, the levelized cost of water was 1.79 euro per cubic meter. That was acceptable considering this production of 100 cubic meters per day in a small scale application. Now, considering the challenge of increase the brightness production, we can consider two different approaches. One of them is that the use of the multi-envelope design that I already discussed previously, that is to produce a higher permit, considering the multi-envelope in the internal design of the model. The other approach is to use another configuration, another design, that is the vacuum with the permanent installation that consists of use several effects in the engine model in order to recover the latent heat of condensation of the previous step. To be honest, this configuration reduces the specific thermal energy consumption, but not too much as, for example, in the other case of the installation from Aquasteel company. But the most important advantage of this configuration is that the recovery ratio in these models is very, very high, considering the normal or the usual recovery ratio of 10 for the installation technology in a single pass. We obtain recovery ratio higher than 50%. And usually, the recovery ratio obtained in this technology is below 10%. And finally, the last channel is to try to increase the quality of the permit. Because when we consider the membrane distillation technology to produce fresh water from seawater, there is no problem because the permit obtained is of high quality. But if we consider the application of the brine concentration, the pore weighting inherent to this technology started to be important. So different approaches have been carried out in order to decrease the pore weighting existing in this technology. One of them is to drain the air gap channel with a low pressure air bladder. The other is to use new membranes doped with compounds that make them more resistant to scaling and also to falling, but also increase the hydrophobicity of the membranes. And the last approach in order to mitigate the pore weighting is to introduce nanobubble in the feed in order to decrease the deposition of the salt in the membrane, decreasing also the scaling, the falling, and increasing the permeable production. And now we move on to the future opportunities regarding the new installation technology. One of them is the small-scale desalination in Ireland and remote areas that already discussed with the successful experience in the membrane installation. The other application is the brine valorization, the brine concentration as a previous step from brine valorization, but generally the brine valorization is considered usually the recovery of the mineral salts from the seawater, but the other way to use the brine is for the energy recovery. Later, I'm going to explain two different projects. One focus on brine mining, but the other focus on the production of energy from the brine. Here we can see the MD model that we already used to brine concentration from salinity concentration from 70 grams per liter to 245 grams per liter. And also we use the vacuum multi-effect membrane installation technology in order to concentrate the basic water up to values of 115 grams per liter. Here we can see the European project Interwatt focused on the production of energy. The membrane distillation was coupled with the reverse electrodialysis in order to regenerate the high salinity stream with the membrane distillation in order to reuse in the reverse electrodialysis to consider the salinity gradient in order to produce the electricity. Here we can see the results obtained with the high salinity, and we obtain a high recovery ratio with this module, and the specific thermal energy consumption is between 260 and 270 kilowatts per hour per cubic meters. Here is the other European project, Sol2H2O. In this case, the membrane distillation system is coupled to the reverse osmosis in order to treat the rejected stream of the reverse osmosis to continue concentration in the membrane distillation as a previous step for the recovery of magnesium and calcium. And finally, the last application for membrane distillation is to produce the high quality water for green hydrogen production. In the green hydrogen production, we consider the technology is the electrolysis. The water is flattened by electrolysis, and this process consumes a high amount of fresh water, not only for the production, but also for the cooling, because the efficiency of the electrolysis is not the 100%, is between 60 and 70%, and this means that part of the electricity is transferred into the heat, and it's necessary to cool down the water to continue the process of the electrolysis. Here we can see also a map of the future of the green hydrogen production, and we can see that the most plant of green hydrogen is located in fronts with water streets, and also is located most of them in areas near to the coast. For that, the combination of membrane distillation with the electrolysis of water is a good combination in order to produce the high purity of water needed to the water slightly, but also to use the waste heat produced in the water electrolysis to heat the process of the membrane distillation process. So we can reach with this combination several advantages. One is that the cooling system is not needed, so we can remove the cooling system. The cost associated to produce water is zero because we use the waste heat of the electrolyzer. And the other is that the electrolyzer can be located in another place far from the freshwater source. So to conclude, we can say that the membrane distillation has a nice application in desalinated water production for island and remote rural coastal community, for brine concentration, for industrial wastewater regeneration, and also to produce the high quality water for applications such as green hydrogen production. The other thing is that the advancement in the membrane distillation technology led to improvement in the performance, energy efficiency, the production, and also permit quality, and new strategy can be adopted to further enhance its performance. And finally, the Aquasteel is the global leader in the field of membrane distillation with several successful products. So that is all from my part. Thank you very much.
I have one question. We have seen numbers from PVRO systems, some numbers from MD systems. Do you see MD getting to the point of being competitive with PVRO?
Competitive with PVRO? No, because I think that the membrane distillation has different application considering the PVRO, because for desalination, MD is not competitive because we cannot reach the values of energy that can reach the PV. But I think. Yes.
So you have presented the value of 1.79
yes.
euros per cubic meter, considering the cost of heat and considering the cost of electricity, which is not so far from numbers. Tony was presented was 1.5. Yeah.
Yes.
For small scale PVRO.
But only in this small scale application. But considering the general application.
Not for large scale. But for small scale systems,
yes.
You say that membrane distillation in solar thermal is already competing with PVRO.
Yes, in this case, yes, can be.
Just one question. Thank you for the very interesting presentation, which is actually the highest production capacity known for membrane distillation for one system.
The problem is that membrane distillation has the trade-off of the specific thermal energy consumption and the permit production. But considering the best ND model that is the Aquasteel, here the specific thermal energy consumption is 43, and the production is more or less of 60 liters per hour.
60 liters.
Only one model, yes, but more models is like the AgroConnect, that is this 6
60
liters per day. Yes.
This is the largest production capacity
Sí,
No.
considering several MD models, yes.
Thank you for the presentation. And you mentioned the problem of salt passage with trick brines, right?
Yes.
But I'm not so concerned about it in the case of circular economy lines, because I think you can recirculate it back in the field of the RO system. So can you give us an idea on the salinity that you can get in the permeate stream, in the condensate stream, when you treat brines?
Yes, depending on the salinity of the feed, yes. But when we increase the salinity of the feed higher than 70 grams per liter, the conductivity of the permeates can be between 100 and 300 microsiemens per centimeter. Yes. But considering MD that in general you can produce a very high quality of permeate, because for seawater the conductivity is 1 or 2 microsiemens per centimeter is very high. Yes, yes.
Thank you so much.
Thank you.
Welcome back after the short coffee break. And now we will start with the presentation. We'll start with Isabel again, who is head of the research unit on water treatment from the Plataforma Solar de Almeria, and who will give a talk on benchmarking on advanced observation processes for water treatment.
Thank you, Elena. Thank you very much. So good morning again, and also good morning for the people that are at home or at their offices. So I'm going to change a little bit, but it's not changing the topic because this is still speaking about water, but not desalination or technologies for desalination. So I'm going to speak more about the wastewater treatment for reusing purposes. But as let's say that in the frame of the project, we are speaking more about photocatalysis and advanced oxidation processes. I'm going to speak about the benchmarking on AOPs, on advanced oxidation processes, more focused maybe on what is maybe more lasting in the time, which is solar heterogeneous photocatalysis and homogeneous photocatalysis. But I would like also to try to give you some guidance for trying to test also and to compare new technologies on wastewater treatment with this benchmarking or state of the art. So as you will see, more or less, I'm following also the content that Juan Antonio did on his presentation. So I will like to adapt a little bit of our topic on the same issue. So I'm not going to be long on this, but just I would like to put you in context so you know, but we are in a high severe drought in the south of Europe, in the Mediterranean countries. So we all know that we need alternative sources of water. So water reuse is already accepted as another alternative water resource, always in combination with desalinated water. So we don't need to, or we need to forget about water or wastewater and think about the effluent of municipal wastewater treatment plants as a resource more than as a waste. And of course, there are a lot of benefits of reusing the urban wastewater after proper treatment. There are benefits from environmental, social, and economic point of view. But I always insist that always in combination with desalinated water, because we don't have enough for all the activities with treated urban wastewater. So we have several challenges for reusing the urban wastewater, and in the other presentations of the other fast track schools, I already explained a lot about this, but I'm not going to go in deeper. We have water microbial contamination, mainly pathogens, but even more important nowadays are the antibiotic-resistant bacteria and genes. We have also chemical contamination coming from, well, normally we have been listening or hearing about contaminants of emerging concern, but now are microcontaminants, and also the more important now are microplastics, mobile and persistent contaminants like PFAS, PFOS. And this is only an example of the quite amount of micro contaminants that we can find in the outlet of a municipal wastewater treatment plant in a very low concentration, that this has an effect when we want to reuse the wastewater. If those contaminants are still there in the effluent of a municipal wastewater treatment plant, and we use them from crop irrigation, then we could be introducing those contaminants in the food chain, but it's a highly important issue from the health point of view. So solar advanced oxidation processes or advanced oxidation processes have been widely studied and even widely applied for the elimination of these contaminants, not only microcontaminants, but also they have been successfully applied for industrial wastewater treatment. These are some of them. These processes are temperature and pressure known, so that you can use them ambient pressure and ambient temperature. And the good thing is that you can drive them by solar energy. Basically, you generate hydroxyl radicals or other radicals that are powerful enough to eliminate contaminants, eliminate microorganisms. So here I leave you some examples that can be powered with solar energy, which is of high interest also in the case of those countries with severe water scarcity. Heterogeneous photocatalysis is the AOP that we use semiconductors, we use catalysts, and we produce, thanks to the photons of the solar energy, not the thermal part of the solar energy, but the photons. Thanks to that energy, we are producing the hydroxyl radicals. You can see some characteristics and also some advantages here. We have also homogeneous photocatalysis by solar photophantom. In this case, everything is soluble in the water. You have iron peroxide, and you use also the solar energy to close the cycle in the iron. So you produce again hydroxyl radicals. The problem with the photophantom process is it's pH dependent, but it is highly adapted to every process. So normally solar photophantom is more efficient than titanium dioxide, of course, even more if we are speaking about industrial wastewater. So following the index of Juan Antonio and the content, the definition of AOP benchmarking would be the same. But of course, if we want to compare with the state of the art, we need to assess several key performance indicators. I must say that these performance indicators are not, let's say this is coming out from the new regulation of the European Commission on minimum water quality for irrigation, and also from our experience. But the point in AOPs on water treatment in these new advanced oxidation processes is that there is nothing yet well established, well standardized. So these are always things based on our long experience. So we normally define different key performance indicators. 80% removal of microcontaminants. This is coming from the Swiss law. This is the only one till now that we have the new Water Framework Directive for Europe that contain or consider the microcontaminants. Of course, we have the specific removal of target pathogens depending on the final use of the water, of the treated water. We have to focus on the dosage of UV radiation, the dosage of oxygen that we are going to use depending on per cubic meter of water, the specific energy consumption, and we need always to apply environmental and health risk assessment. And of course, when we are trying to define the best treatment solution, we have to go through the life cycle assessment. So if we do the SWOT analysis for the advanced oxidation processes in general, we have the strengths, weaknesses, opportunities, and threats. Of course, we have the strengths that the catalyst is regenerated. You can operate with solar energy. We have, as I told you, restrictions on the pH. It's a weakness. Of course, we have the generation of sludge if we use solar photophantom because we have iron, and when you change the pH, the iron precipitates as iron hydroxide. So you have some sludge. Even more if you have industrial wastewater, but we have several opportunities because we can try to produce new semiconductors, trying to use also ligands to be able to work at neutral pH. And of course, we have the dependence on the light. And normally for this kind of advanced oxidation processes, the higher costs are in reagents, and but not so much the energy if you use, of course, solar energy. If we go through the SWOT analysis for the heterogeneous photocatalysis specifically, which is what we are more focused on this project, we have the favorable conditions and properties of the catalyst. We have also simultaneous disinfection. At the same time, we eliminate contaminants. But we have some weaknesses because we have limitations because normally titanium dioxide and other semiconductors are only active under the UV part of the solar energy, but not the visible part. So there are a lot of new studies on trying to improve their activation under visible light. The good thing is that we can now design new photoreactors, thinking on immobilizing the photocatalysts on different supports. And of course, we always can use the LED as a technology instead of solar energy. Of course, we can reuse the catalyst, but if you don't support the catalyst in an immobilized system, that require also extra steps and extra costs. So which are the challenges and barriers for the AOP implementation and the penetration to the market? Why? Because we cannot say that we are in the market yet. There are not big companies producing AOP systems. Why? Because normally even more the solar systems, the AOP systems, are more used for specific industrial wastewater or for decentralized systems. So we have a lot of small companies working on that and giving those solutions so you can obtain it in the market, but it is not broad spread in the market. There are different challenges and barriers. There are technical challenges. I was mentioning that titanium dioxide can use only UV, but not the visible part of the light. Photophantom is pH dependent, so you generate a sludge. You have to be careful with the transformation products that are generated after the process because they could be more toxic than the parent ones, so that could be a problem. Of course, we need to perform studies first, maybe with simulated wastewater, but we need always to conduct experiments and tests with real wastewater, and that's always a challenge there because you have a complex water matrix that is also using the hydroxyl radicals that you require for the contaminants. So you have also some economic barriers or challenges in the capital investment and operational costs, depending on the wastewater you are going to treat. But the good thing is that at least if you are trying to use this kind of AOPs for the solution to industrial wastewater, you can integrate different technologies, so then you reduce operating costs in that part. Of course, the regulatory framework is highly important. Actually, now we have let's say, it's quite fancy, these advanced oxidation processes, because now we have quite a strengthened regulatory framework coming from the European Commission for treating the urban wastewater and reusing them, and also for reducing the water footprint in the industry. So now we have this framework that helps us to implement the technology. And of course, public and the stakeholders' perception and acceptance is quite important for us because we are reusing the urban wastewater, and that's not quite fancy for the public. But now we are doing quite effort on translating them, what are we doing, and to show them the good resources that could be used with urban wastewater, and they are understanding now, and things are changing a lot on that side also. Within these challenges and barriers in the implementation of the technology, I wanted to stress you and highlight you this that I was mentioning before. We don't have we have a lot of official standards for the measurement of the physical-chemical characteristics of a wastewater, for measuring TOC, COD, anions, statins, or whatever. We have a lot, but we don't have standard procedures to compare different technologies in water treatment. They are not a standard. So all of the people that work or companies that work on that, we know how we can compare. There are a few publications, but there are not standards yet. And that's even a problem, of course. Well, I leave you this here. I'm not going in deep because it's only how to compare. These are the guidelines I was telling you. We don't have standards, but there are some publications and they give us guidelines to compare new AOPs or new technologies with the state of the art and with benchmarking technologies. Of course, they are speaking always on the, depending on the wastewater, the contaminants you are going to target, the wastewater you are going to target, the scale you are going to be able to apply your new technology. You have also to define properly which is this final application and which is the benchmark you are going to compare with. Of course, you have to always use real wastewater to optimize your new technology and to compare with the state of the art. And always you have to compare the energy and the cost efficiency because that's quite important. Even when you are going to scale up and you're going to use solar energy, you need to apply or to design new photoreactors, and that's also quite high costly in investment if you don't decide properly which is the reactor that you are going to use. That can increase a lot the costs. And of course, always after it's a decision diagram in which at the end, if the new AOP excess over the benchmark, then it's better to change it, of course, and to try to modify it. So as it is not well established in the market, let's say, few of the technologies, yes, but not AOP. I'm going to show you some successful experiences, but focused on the TRL. Where are we? This is a diagram in which I show you the different, or a classification of the different AOPs. Some of them are already in the market. You see established full scale, it's in green. Let's see that pilot scale in orange and developed at large scale in green. So those in green are established at full scale. Of course, we all know ozonation. Ozonation can be an AOP when you combine with hydrogen peroxide or when you combine with solar energy or with other catalysts. I put you here some pilot plant pictures coming from the PSA, but it's also tested at full scale. We have also the UV systems, of course. They are already implemented as tertiary treatments in wastewater treatment plants, but you can improve their efficiency adding chloride or with peroxide or other oxidants. And that's also in full scale, though I put you here pictures from the PSA, but it's also implemented. Photophantom and also the thermal activation of persulfate, which is also an oxidant that can do both things and can produce sulfate radicals that can eliminate contaminants. Both have been tested already at full scale. I will show you some demo sites. Here is only a picture of the CPC, but also here you have to take into account which kind of wastewater are you going to treat, always, because if not, you are going to have a high implementation cost or high installation costs. So if we focus on the TRL, we are going to focus from 4 to 7. In the 4 is lab testing validation, so the design, developing, and lab testing of components and also new AOPs. We have already tested between TRL 5, 6, the treatment of industrial wastewater. This is an example on landfill leachate. And here, as I told you, we are integrating or combining different technologies because our aim is to reduce the costs due to the AOP, and we only use AOP when it is highly necessary. So for that, we have to prepare the industrial wastewater. It's a coagulation, flocculation, physical-chemical pretreatment. You eliminate solids, you eliminate color. Then you can apply a solar AOP because you have a more or less transparent or less colored industrial wastewater. So you reduce the consumption of oxidants, you reduce the cost, and even as soon as you attain a high biodegradability, you can combine with a biological treatment. This is what we have been doing. And we already have costs for that. Of course, these costs are for industrial wastewater treatment, so they are not cheap. If we go through to the treatment or the elimination of microcontaminants and microorganisms in the outlet of a municipal wastewater treatment plant, the water is clean. you don't need the integration of those treatments. This is the calculation basis, more or less, and we are comparing ozonation, which is commercial, with solar photophantom. Our surprise, let's see, in that time, it's that they are competitive, though. Why? Because ozonation, of course, if you don't, let's say, if you don't care about the dosage of ozone and you don't care of the solubility of ozone from the gas to the liquid phase, transfer, then you are spending a lot of money on that. So the cost increases. The other alternative also is integrating also for the elimination of microcontaminants in the urban wastewater treatment plant. If you put a nanofiltration previously, you can pre-concentrate the outlet on microcontaminants. So then when you treat with the AOPs, you reduce the consumption also of energy and of oxidants, because you are increasing the concentration of contaminants and you're reducing the amount of water you want to treat. So here we compare when we combine with the nanofiltration pretreatment or not. And if we go through to the TRL higher, 7, 6, and 7, so we go to the prototype demonstration and also the demo site demonstration and validation in a real scale and real environment and a scenario. We have been already treating the effluent of a municipal wastewater treatment plant. Here we compare solar hydrogen peroxide with solar photophantom, which is an AOP. Solar hydrogen peroxide is a photochemical system, but not an AOP. And we have been irrigating lettuce and radish, and we were checking what happened with the contaminants and the pathogens. So it was in a real scale greenhouse. We have also the examples of demo scale 6 photoreactors for the treatment of, in this case, was the elimination of the contaminants coming from the washing of the pesticides containers for reusing the water. So this is the construction of the treatment field. It was something like 150 square meters and different modules of CPC. And well, in this case, we also did the validation of the solar photophantom here. In the case of upscaling, what we have been also learning in the case of demo sites is that it's worthy using this from the economical point of view when you have industrial wastewater, as I told you. But when we are dealing with urban wastewater, which is much cleaner, you can use cheaper photoreactors. And these are the raceway pond reactors that have been used for a long time. These are commercial for the growing of microalgae. In the University of Almeria are experts on this. They have been implementing this technology in the wastewater treatment plant in Almeria with Aqualia. So we will have a colleague from Aqualia speaking afterwards also. And these are very cheap, so you can have this wastewater there because it's not toxic, so it's better. You are going to have less expensive implementation costs. And we have been also implementing them at demo scale in another wastewater treatment plant, Mesamor, in the southeast of Spain, in Murcia, also with very good results. In our case, we are not using solar photophantom. We are using solar photochemistry, solar hydrogen peroxide, solar PBS. The University of Almeria is using with Aqualia solar photophantom, so we can now compare the costs and we do a life cycle assessment problem. Future opportunities. The thing is, for us, the future opportunities, or even say nowadays opportunities, are focused on that we need the water. We need to treat all the urban wastewater for being reused in crops irrigation, because we consume 90% of the water is consumed in the irrigation. And also the reduction of water footprint, industrial water footprint, is quite important nowadays. So we can improve, we have the opportunities on lowering the costs of the photoreactors, as I show you, depending on the application we are going to tackle and to face. We can have new solar immobilized photocatalysts. So of course, solar photophantom is more efficient, but if we deal with supporting the catalyst, highly efficient catalyst and immobilized in a support, then we can also use them because we can use a lower amount. And they are also efficient because we need less amount of energy for microcontaminants elimination. We are also investigating a lot in new membranes for photocatalytic membranes for doing both things at the same time, nanofiltration or ultrafiltration. Of course, the digitalization of the water sector is quite important. We are collaborating a lot with people that are doing the decision support tools based on machine learning systems. The government initiatives, we know now that we have new regulations, the new Water Framework Directive. We are also focusing on complying with PV, at least to try to reduce costs on energy, though our costs for energy are quite low. And of course, we are always focused on the water energy food nexus for the food production and the reuse of urban wastewater also in aquaponics, which is quite nowadays. So I think I'm concluding now, so maybe more or less I didn't pass a lot. So just a few conclusions to remind you that AOPs, solar AOPs based on photocatalysis have their market niche in decentralized systems, isolated areas normally, or specific industrial wastewater treatment. You need to validate always the new AOPs, new technologies with actual wastewater, real wastewater, and also under the real operating conditions or environment. And of course, the longevity of these new treatments materials have not been tested yet. We need longer time, and it depends on the water matrix. And for me, what is highly important is the integration of the wastewater reuse into the circular models, and the circular economy is quite important. It's being done nowadays. And for that, the health risk assessment and the life cycle assessment must be also included. And just to finish, sustainable aspects should be always taken into account. And also the water positive initiative and the social. So that's all from myself. Thank you very much. I don't know, some maybe curiosity. So I know it's not your topic at all. Yeah.
You mentioned the possibility for removing microcontaminants through nanofiltration, concentration. What about FAS? Which are very
what about
the normal kind of contaminant, which is very focused.
I don't know which contaminant is that. PFAS. Yeah, I told you. Yes, you can also. We have not tested yet the pre-concentration of the PFAS with nanofiltration. We are working on that now. But those technologies can eliminate them. The thing on PFAS is that there are some that are not oxidative. You can reduce them to transform them to another contaminant to oxidate. And we are working also on the combination of reduction and oxidation technologies for that. Yeah, but they can.
That would be a very good market.
We are focusing on that. Also with but it's not a good market, it's microplastics. Everybody is focused on microplastics, and AOPs only reduces the size of the microplastic, but you don't destroy them as expected.
Since we are talking about desalination, we have an experience of post treatment of permeate water, that usually before human consumption, the desalinated water is.
Well, actually, Alba did some work with us, treating after MD, also checking what's happening with the E. coli, with the pathogens, and it was successful also. But we have not done a lot yet. So the idea, of course, the thing is nowadays, what is in the market, as far as I know, in desalination is a reverse osmosis. What you have in the outlet, it's the still water, so demineralized water completely. So at that point, that the permeate is perfect. The concentrate is what we have not checked yet, what's happening with that. We have been working a lot with high salinity wastewaters, till 40 grams per liter of chlorine, so quite high. And solar phytoplankton is also efficient on that. So this is also, there are also opportunities there, I think. Thank you so much.
Thank you so much. Our next talk will be given by Andrea Giannina from the University of Palermo. And he will speak about the benchmarking on zero liquid discharge technologies.
Yes, thank you, Elena. So, zero liquid discharge. It's not easy to make a benchmarking on zero liquid discharge because zero liquid discharge is not a technology. It's a kind of general strategy or a philosophy of implementing different technologies for reaching a goal. And in fact, zero liquid discharge desalination aims at eliminating all liquid waste from the desalination plants, recovering valuable resources. But the main driver of zero liquid discharge is an environmental driver. So you need to eliminate the problem of brine discharge. Key features: we aim at a recovery of almost 100% of the water. We need to produce solid and dry salts instead of a liquid brine. And these processes are typically very, very energy intensive and cost impacting. This is why I was mentioning the main driver is an environmental driver. The technologies involved are reverse osmosis or other desalination technologies for the first step, brine concentration technologies that can be membrane separation or thermal evaporation, crystallization technologies, electrochemical conversion technologies. But there is a difference between zero liquid discharge and brine mining, which is maybe closer to the concept of minimum liquid discharge. In fact, in this second case, we have a different aim. The aim is to recover valuable resources from brines, but limiting the focus to what is economically viable to recover. So the key features are you recover only the compounds valuable for internal use within the same plant or valuable for the market. Again, produces solids or specific salts, concentrated solution that have a marketable value. But you still require a brine discharge mitigation strategy. You do not eliminate at all the brine disposal problem. You need to face it in some different way. The technologies are very similar to what you have in zero liquid discharge. So you have brine concentration separation technologies, other type of separation technologies such as liquid gas conductors in some cases, crystallization, and electrochemical conversion. But what makes the big difference between ZLD and MLD is that in MLD, so in brine mining or minimum liquid discharge, you have two drivers. One is the environmental, the second one is the economic. That may weigh more than the environmental. In Sol2Water project, as you all know, we are implementing a zero liquid discharge because after the PV reverse osmosis desalination, the brine is treated in order to remove magnesium and calcium or bivalent cations. And then we further concentrate it in membrane distillation, the membrane distillation unit, to produce additional water and further concentrate in the brine. And then the brine goes to two solar ponds where sodium chloride, marketable sodium chloride is produced. But in the last one, we just aim at eliminating completely any liquid waste. Now, as I said, it's not easy to make a benchmarking, but we can still define for zero liquid discharge some key performance indicators, some main parameters that can identify the performance of this process. The benchmarking for ZLD and brine mining should be to identify the best performing technologies for different brine composition and different brine origin, and also identify industrial synergies. As I said, we have to implement an integrated process, so it's much more important to see which can be the synergies with other industrial processes nearby and specify the origin and composition of the brine. Optimize process schemes and recovery strategies for energy savings and cost reduction. But in this case, a very important keyword is circularity. In many cases, zero liquid discharge or minimum liquid discharge strategies work very well if you implement a fully circular scheme. Guide investment decisions in sustainable desalination projects. Now, the comparative analysis between different approaches, different strategies can be done based on 4 different classes of indicators: energy intensity, technological readiness level, overall recovery and circularity potential of the integrated approach, and economical benefits of the brine mining activity. We will quickly look at these classes. So energy intensity, can I move it? Energy intensity of the LP or brine mining process. We can define 2 different types of indicators. Energy indicators relevant to water separation. Typically, we have a specific energy consumption for the desalination phase, or a specific energy consumption for the brine concentration phase. But we can also identify energy indicators relevant to the mineral compounds. In this case, it's not only that we want to produce water, we also want to extract a compound, solid or a solution. And in this case, we can define a specific energy consumption for the produced compounds, defined as kilowatt-hour per, for example, ton or kilogram of the compound. And then we have the concept of technology readiness level, which is very well known to all of you. So TRL depends, and let's say the benchmarking can depend on the capacity of the largest operating pilot plant, demonstrated operational time of pilot plant, number of implementations. The other 2 classes are overall recovery and circularity potential of the integrated approach. And we have several, well, we have much more key performance indicators, but these are the most used. Resource efficiency, how much compounds you have recovered compared to the same compounds arriving with the incoming brine. Circular chemical inflow, which tells you the kilogram of recovered species that are reused within the process itself, divided by the total chemicals that are used in the process. Energy self-sufficiency, which is especially important when you have recovery of waste heat, for example. You want to know how much of the energy you consume comes from the waste heat, or from integration with PV or wind systems when you are using excess electricity that is produced in peak hours. And finally, economical benefits of the brine mining. So we need to know the CAPEX, OPEX, but we can define specific parameters like levelized cost of the treated brine or levelized cost of the produced chemical. Now, as I said, this will not be a benchmarking of zero liquid discharge technology, but we can say that in order to implement zero liquid discharge, we need to have brine concentration technologies and, let's say, solid separation technologies. So we will make a quick comparison of brine concentration processes, which are listed and classified in membrane-based, non-membrane-based. And there is a long list. You may remember this list was already discussed during the first fast track school. So I will just fly on that and on the following slides, because apart from a couple of you, the others have already attended the list, but you can find in the slides and also in an annex backup slides with all the information that you would like to have. So we classify these brine concentration processes, and we start with the pressure-based or combined processes like high-pressure reverse osmosis, pressure-added osmosis, nanofiltration for brine management, ORO, and so on. And I'll show you just as an example a graph indicating the energy consumption in kilowatt-hour per cubic meter of treated solution. And as you can see,
the values can change significantly, going from few kilowatt hours per cubic meter up to 15 kilowatt hours per cubic meter with very large deviations, because they also depend on the technology and on the type of brine treatment. But worth mentioning that these values refer to different type of brines that we are concentrating. Lower values to lower concentrations, highest values to highest concentration. But this was just to tell you, if you want to really concentrate a brine above the threshold of, let's say, 100 grams per liter, you need to take into account that the energy consumption will be 10 times higher than typical energy consumption of brackish water desalination or even seawater desalination. When you go from pressure-driven to thermal-driven processes, as Alba has already shown, you change by at least one order of magnitude, in some cases, depending on the technology, by 2 orders of magnitude energy consumption. But this is thermal energy consumption, which is cheaper than electricity and can be recovered by from waste heat or solar thermal. About the technology readiness level, most of these technologies have achieved already the pilot scale testing, so at TRL6. Some of them are already above, so pilot plants being demonstrated in real environment with good automation level. In some cases, like high pressure reverse osmosis, we are talking about an industrial technology, well proven. Electro-based process, high salinity electrodialysis, electrodialysis metathesis, reverse electrodialysis. How are located these technologies in terms of energy consumption? Again, we have a big variation which follows the trend of salinity. The highest values are between 10 and 20, 25 kilowatt hours per cubic meter. Again, very high values, but they refer to highly concentrated value. Of course, in the reverse electrodialysis, as well as in the pressure retarded osmosis in the previous graph, you have a negative energy consumption because these are technologies producing electricity from saline gradients. TRL 6, 7, not very different from the previous case. Thermal basis processes, relatively low electrical energy consumption, but we have typically very high thermal energy consumptions. A big variation in the case of the objective crystallization process, for example, which is still a pilot scale technology. There are 6, which in the literature are reported very, very variable results. So you can find much more information in the backup slides that you can download from the website. Same for crystallizers. You can have a huge number of crystallizer configurations, operating conditions, and so on. From the conventional ones, sorry, it should be a bit lower, to the most innovative ones. In the Fast Track School 1 and 2, we have already analyzed and discussed 2 types of crystallizers: the multiple feed Plateau reactor, which is being used for magnesium recovery, and evaporating solar ponds that have been used in zero liquid discharge schemes for recovering sodium chloride. But just flying over different possibilities of conventional crystallizer, PVXs, semi-batch, double feed semi-batch, we have continuous crystallizer. And this is what we've seen about multiple feed Plateau reactor, which is a technology patented by resources. Fabrizio may give later on a presentation more focus on that, which has been applied in a number of research projects, reaching a quite good TRL level of between 6 and 7, with different types of applications. And also about evaporative ponds, we have discussed it a bit. You have to make, basically, if you want to get good product quality, you have to make fractionated crystallization, which means you evaporate and concentrate the brine under multiple following steps until you reach the saturation in, first of all, calcium ions, typically, calcium salts, and then sodium chloride, which is your final component. You need to know very well the crystallization kinetics in order to properly design the system, but this can be done, and it was demonstrated, and Lorenzo presented something in the last track school. You can demonstrate that you can produce very high quality sodium chloride in a very simple way. Now, I'll go through a couple of examples of implementation. The water mining project, I mentioned it in the last track school. What I want to show you is what is presented in this recently published paper. It's an analysis showing performance indicators and circularity indicators of this integrated process that is basically a full zero liquid discharge example. How does it work? We start with seawater, nanofiltration separates a latent tape, which is rich in bivalent cations and anions. MFPFR reactor separates magnesium and calcium in the form of hydroxide ions. And the effluent, which is calcium magnesium free, can be treated in an electrochemical device for the conversion of salt into sodium hydroxide hydrochloric acid. Sodium hydroxide is fully reused within the process itself. The remaining brine can be further treated in the MED plant. There is a missing arrow here. The permeate from the nanofiltration instead, which contains mostly monovalent ions, can be treated in a multiple effect distillation unit, producing high quality drinking water and being almost fully powered by waste heat. The net brine, which is very concentrated, above 200 grams per liter, can fill the evaporative ponds where sodium chloride is produced. These are the pictures of all the units, nanofiltration inside a container. This is the net evaporation unit. These are the solar crystallizers with the salt precipitated in the bottom, MFPFR, and ETPM units. So all these pilot units were implemented, they were operated, data was collected, and this is a summary of the results. Purity of solids produced. High purity obtained for magnesium hydroxide. You see, it changes between 90% to 98%. We reached also higher value. And the difference that depends on a very specific factor, which is the presence of a pre-treatment of the brine, which I will show you in the next example. Calcium hydroxide purity is lower because of the co-precipitation of magnesium. But that's not a big issue, as I will explain you. Sodium chloride, very high purity. This is much better than food grade sodium chloride, which is the recovery of products, up to almost 100% for magnesium, between 70 and 80% for calcium, above 95% for sodium chloride. Some of it is lost with the mixed salt at the end of the chain. And from 70 to 85% recovery of water. So very high recovery of water. But we also produce some chemicals, in particular sodium hydroxide and hydrochloric acid solutions with a concentration between 0.5 and 1 molar. Circularity indicators. Resource efficiency, circular chemical inflow, energy self-sufficiency, we have defined them before. And this table summarizes which values were achieved. And there is another one, the total brine reduction, 93% of reduction in the brine volume. Resource efficiency for water, 80% of water recovery. Product purity, which is not about circularity, but a performance indicator. We could see 90%, 100% for magnesium. We have seen it in the previous Instagram. But what is interesting, circular chemical inflow, 100%. In this process, we needed chemicals, but all the chemicals we needed were produced in situ. So there is no chemicals coming from outside. Energy self-sufficiency, 85%, because most of the heat for the MED, the energy for the MED unit comes from waste heat. and we only need electricity from the grid. That is a second example of the project. I finished my 20 minutes, but I will go fast through the conclusions. Brine to Value project. It's somehow the continuation of the water mining, but we wanted to demonstrate that with the similar units, cutting what is most energy expensive and also cost intensive, we can still achieve a nice integration of processes for brine mining. The objective in this case is not zero liquid discharge, but it's brine mining for internal use. And this is the process scheme. You have your brine, you take a portion of it, and you have a first step for CO2 removal. Why CO2 removal? Because the final goal is to obtain from this process what you need for remineralization. So CO2 is needed for permanent remineralization. But the second reason is that if you remove CO2, you get better quality in the reactive crystallizer because you avoid the precipitation of calcium carbonate with magnesium hydroxide. Reactive crystallizer, separation of magnesium hydroxide. Second reactive crystallizer, where you have a final crystallization of a mix of calcium and magnesium, again useful for permanent remineralization. Okay? Finally, you have EDBM closing the loop and producing what you need, the chemicals you need for acidification before CO2 removal and alkaline reactants for the crystallizer. The process has been implemented at full pilot scale, semi-industrial scale, to be honest, and the units are all operated now. I'll show you some results only from the MFTFR crystallizer, just to highlight how the purity of magnesium hydroxide dramatically changes, passing from the standard configuration with no CO2 removal, 93, 94, 95%, to a purity above 98% when you remove CO2. Okay. Challenges about zero liquid discharge. Very large energy consumption for brine concentration. The answer is adopt natural solar evaporation where possible. Develop more efficient membrane concentration systems. We are waiting for that. Or separate minerals from brine directly without concentrating the brine. But this gives us a different answer. We are not going to zero liquid discharge, but to brine mining phyllogen. Purity of solid products does not meet the market targets. So that means you have to implement fractionated crystallization schemes, adopt selective reactive crystallization as a technology, or use membrane-based pretreatments for ions separation. Finally, large footprint requirements for solar evaporation ponds. How can bypass it? Implement pre-concentration stage, adopt technologies achieving higher evaporation rates, or renounce to zero liquid discharge and go for just brine mining. But we also have some economic challenges which you will address in the workshop in the afternoon. The first of all is high cost of chemicals for reactive crystallization. And the answer is implement circular schemes for in situ generation of chemicals. That reduces dramatically the cost. High cost of energy, waste heat, renewable energies. And these 2 points are very important. High production of costs of salts and minerals. Okay? You have to adopt a value-oriented design of the brine mining strategy. Just recover what is valuable and in a way that makes it valuable. And second point is excess production of salts minerals. Adopt a market-oriented design of the brine mining strategy. Just produce, just mine what you can actually sell in the market. Okay, I can skip the conclusions because they are a summary of what I said already. And that's all.
Thank you. Hello again. Can we restart already our fast track school? So now we'll have the presentation by Bart's elements from Atlas Field on the exploitation contents and market opportunities on MD. Okay.
Hello, Bart.
Yes, I'm here, but I'm trying to share my screen, so I don't know if that's
It's
happening
working. Yeah, just need to put it in presentation mode. And,
now. One moment.
F5.
Yes, now we are there, I think.
Yeah. Great. Thanks so much. So the floor is yours. Thank you.
Thank you. Good afternoon, everybody. Yeah, I couldn't be there. I'm sorry for that. We are quite busy with some kind of new development. But what I understood from the request last week is that I would give you a short presentation about membrane distillation, which kind of challenges we are facing with our technology, especially compared to the thermal heat we need. And then at the end, I also have some examples on what we're working on right now, which are quite differentiated. But first of all, I want to talk about a little bit about membrane distillation because it's not everybody that's new with this technology. At Aquatil, we are working on membrane distillation for almost 20 years now. And the principle is quite simple because it's a thermal evaporation technology where you need a waste heat source and of course a cooling source because you need a temperature difference, because you need a pressure difference over a membrane. So it's thermal desalination where you also use a membrane. And the membrane in this case is hydrophobic. So that means that liquids are not going through the membrane, but vapor and gas can go through. So you have different kind of membrane configurations. The most simple one is direct contact MD, where you use two channels, a hot one and a cold one, and in between there's the membrane. That's the most commonly used in university because it's quite a simple setup. But it's not always the best setup because you are facing some issues with heat and mass transfer. So to diminish the heat losses over the membrane, there's another configuration you can use, and that's air gap membrane distillation, where you add not only the membrane, but also a kind of air gap where you can collect your vapor, and that will condense against a condenser. And this way, it's more easy to produce clean water. And the second advantage is you have better mass transfer and also less heat losses to the other side. Then in the number of years we were working on it, we evolved even further because then we said, okay, when we make the pressure lower in the air gap and in the membrane, that means that you can increase your mass transfer. So it's a higher flux, as we call it, and more distillate production. And at the same time, it's a better insulator. So your energy performance also can go up then. So these are three main MD configurations we worked on in the past. We're now working on a fourth one, but that I will present at the EDS. So, but when you're facing membrane distillation, you have several challenges. One is, of course, your energy consumption, because it's a thermal desalination technology. But another problem you face when you're building systems, it's not easy because you need to have a system that's leak tight. So you need some glues or way of tightening your envelopes. And it often causes problems because you're not only using a glue, but you also have to have a glue that is resistant against quite high temperatures, 80 degrees or more. So then 80% of your glues will not work. That's a side note. But besides that, you also have to construct something. And you have several ways to do that. The first one is, in this case, plate and frame. So you put a number of spaces and a number of membranes on top of each other, and you place it between two plates. And you try to pressurize it in such a way that it doesn't leak. But you need quite heavy structures because you want to keep your pressure inside. So I'm not a fan of that one. I tried that for many years. The second way is to use tubular systems or capillary membranes. But then it becomes quite easy because then you have to put a membrane and a condenser together in a system, which is also not that easy. And furthermore, your hydraulic pressure losses are larger than in envelope systems. So therefore, we're also not using that. And we went to the third option, and that's the spiral wound, where you combine flat sheet membranes and spacers in a system that is cylindrical. So it's easier to keep your pressure inside. So it's easier to maintain all the fluids inside, so you don't have leakages. So on the spiral wound module, you can use different ways of building it. Yes. You can imagine that you have several spacers. It's a kind of filling of an envelope. And you can, what we do is typically we use one foil and we go several times over the spacer, like a zigzag structure. So that you see on the left side. And when you do that, you simply build a heat exchanger. So there you can learn a lot about your heat transfer inside channels, for instance. But what if you replace this foil with a membrane, then you have this direct contact membrane installation module, which I've spoken before, but you still face a lot of heat losses. So when you want to go to the air gap MD system, and that's the third picture I try to put down here, is when you combine a foil and a membrane, and in between is space, an air gap spacer, then you typically have an air gap membrane distillation module. So in practice, that means that you have a cylindrical shaped module. And when you play around, and that's the best way to consider when you imagine a heat exchanger, and you make this heat exchanger longer, it becomes more energy efficient. But when you make it shorter, you have a higher heat transfer per square meter. And that's the same story in MD. So we can play around in our configuration with the length of the envelope, and with that we can increase or decrease the energy consumption, and we also increase or decrease the flux or the production. And that's important for several applications. So I come back to that further on. To finish this story about how to build modules, here we also, in this module, it's also possible to add some vacuum to the air gap. So we have all the advantages of insulating and having decrease the mass transfer inside modules. So there are some lessons learned, but that's, for me, it's almost 20 years experience. But plate frame modules and tubular modules, we don't do. Maybe a tubular module when you go to really high salinities, but the spiral modules are, in our case, the best one. And then you look at air gap and vacuum air gap or vacuum assisted air gap it is, systems. And the longer the envelopes, the better the energy efficiency. And we normally take a GOR, gain output ratio, as a number for that. But longer envelopes will give you lower fluxes. When you have adding a vacuum, you can increase the GOR and the flux, which is pictured in this graph. The flux is the production of distillates, and the GOR is the energy efficiency. So what you want is, in the direction of the arrow, you want a higher flux, because that means lower capex, and you want higher GOR values, because that means that your system is more energy efficient. So one way to do that, already mentioned, is adding some vacuum to your air gap. But we are still looking for other options to optimize our systems. The thing is, when you add a vacuum, you're also adding a risk, because the risk is that you have bigger hydraulic pressure differences over the membrane, but also in and outside of the module. So when you really want to optimize, and we did that also in the past, but we're still working on it, it's modeling, it's simulation. It's making a model, describing your heat transfer inside channels, describing the mass transfer inside membranes, and also the heat transfer, and also the mass and heat transfer inside air gap channels systems. And this is a bit of a small overview of what we do with the modeling. It's quite complicated, but you have, of course, some input values like physical data, material data, configurations, and then you have your mathematical model that can calculate everything. And the outputs for us are three important ones. That's flux, because that will determine your Kpax on the system. So the lower the flux, the bigger the system has to be. And the second and the third one is GOR and electrical energy consumption. So you have the stack and the SEEC, I believe. But it's your thermal energy consumption and your electrical energy consumption. The thermal is what I just described. As you need some temperature difference for the module. The electricity consumption comes from circulating your fluids through the modules. And when you take a spacer, for instance, that has a really good turbulence promoter, because that's what it is, then you have high pressure losses. But that was also translated in higher cost of electricity consumption. So it's trade-off between flux and thermal energy consumption. And on the sideline, it's also choosing the right materials for inside your channels. So we always try to optimize that for every situation, every application you will face. So one of the things, and it was one of the questions I remember from last week, is, okay, what are the challenges? What are the biggest opportunities to improve these systems? And personally, I think when I go back to the sheet, when you look at the temperature profile, in red, it is the temperature profile inside your channels. It's the transfer from the middle of the channel to the membrane or to the condenser. That's quite big. And where you want to have this big temperature difference is over the membrane and the air gap, because there you need it for the mass transfer. So you have to diminish the temperature, the delta T inside spacers. So therefore, spacer optimization is for me the biggest thing to look into. And you can think about that when I don't have a picture here of a spacer, but you can think about the filaments on top of each other can be thinner. So you do reduce pressure losses, can be non-woven structures. You can play around with the distance between the filaments. So surely you can play around. You can do 3D printing, but that's in practice a bit expensive for bigger modules, of course. But you can evolve in new ideas how to do spacer designs. And one example is the tagliatella structures of a professor in Germany is talking about, where you flip around every fluid every few millimeters. So it's flipping around the cold top side to the bottom to the membrane and vice versa. So, and I think CFD modeling can do a big job finding new spacer designs for our application. Another thing I didn't mention about membrane distillation, we now looked at flux and thermal heat consumption and also electrical consumption. This is more we call it the quantitative aspects, but you also have a quality aspects in MD, because you can have leakage through a membrane and you have several kinds of leakages possible. It can be pinholes, it can be the wetting of the membrane in this case. And here you see a picture of recently bought equipment where we can really show not only that a membrane will wet, but also the moment where it wets. And that's important because then you can determine your philosophy how to solve this issue, because wetting is liquid can go through this hydrophobic membrane at that time. Because hydrophobicity went down, you can have a surfactant in your fluids, for instance. So you can prevent that going in. you can increase your hydrophobicity of your membrane itself, so it's more resistant against wetting. You can decrease pore sizes, you can decrease the pore size distribution, for instance. You can lower your operation temperature, but that's an issue because you want high temperatures in your modules because that's your driving force. You can clean more often. So that are all kind of aspects we are facing in practice, not on lab scale, but really in practical applications. So we always have to take that in consideration. So one of the European projects we're now working on better membranes is the Super Clean project, where we test several membranes that, for instance, are treated with plasma treatment or something like that. So we're really involved also in the membrane development, but more on the quality aspects, because I don't believe there's much to gain in quantitative aspects to increase flux, for instance. So the other side, this was more about the modules and how we build them and all the things we consider. Then the other side of a company is that you also have to find applications where you use this technology. So this is a general overview, but the main thing here is you need water which contains some salt, and you have to take it out. You have to take it out or you have to concentrate it. So you can go for really clean water with this application. And then you talk about water that you can use for hydrogen production, for instance. You can also look at the other side and say, I am not really interested in the clean water, I'm interested in the concentrate. So for instance, when you talk about produced water, they have to truck the dirty water out from the location. And then you can say, hey, when I can concentrate by a factor of 2, I have to ship out half of the volume of water. So it's all depending on the application, what you want. If you're interested in the concentrate or the distillate, and if you have enough heat available on site, that also determines all these factors on the design of the module itself. So I have some applications where we work on right now. One is in the Caribbean. That's the biggest one we are operating right now. It's almost 2 years now. We had some child diseases to kill, but now it's running since August without any interference from our side. But this membrane distillation unit is connected to a diesel generator, which is normally producing electricity or reverse osmosis. But we are using the waste heat of this genset to power our membrane distillation unit. And on the other side, we have the cooling water, it's the seawater. And with that, we can produce potable drinking water for resort. So that's one application where you can say overall you can diminish the amount of electricity you're using, because you need less electricity for the MD unit than for the reverse osmosis, and producing the same amount of water. So that's one of the applications we are doing right now. Here are some results and a picture of the resort itself, of course, but also on the installation, which is containerized, and some values inside. So this is one of the applications where we can say, okay, we have heat from the genset, and we can take quite a lot for that. So we can reduce the envelope length, and we can go for a bit higher fluxes and a bit lower GOR values. This is another example, but what I wanted to say here is when you typically look at solar applications, investing in a solar field is quite expensive, I think, when you want to produce heat. So thermal solar collectors, for instance, and then you have to be really careful using this heat. So there you have more attention to high GORs and a bit lower fluxes to have a business case. So that's the trade-off every time between flux and GOR. And that's the most challenging thing in MD, I think. Back to another example, and this is one of the things we did 2 years ago, and we did before project. But here we're combining the production of hydrogen together with membrane distillation. And MD is here used to really produce clean water for the PAM stack, as they call it. And the nice thing about a PAM stack, it's producing heat. So I have raised heat available, and at sea you have also cooling water available. So we call it, imagine, hydrogen oven in this case. But it's working because we were able to produce really clean water that was of better quality than reverse osmosis can produce in two steps. Two pass reverse osmosis produce less quality water than one step membrane distillation in this case. But the thing is, and that was also one of the subjects in this meeting, I think, the challenges you are facing. In this case, hydrogen, it was coming up 2 years ago. Everybody wanted to work on renewable energy and that kind of things, but political climate is shifting. So now it's more out of the picture. So that's the things we're also facing with the application. Then you think you have a good application, as in this example, and then political shifts will give you bad times. So that's always the case we are facing when you are a company. Here you have some photos of the projects. The middle one is in India, producing clean water, and the other one was at North Sea water in the Netherlands. And yeah, so it still can be used in better times, I think. So here we have some results. So we also worked here for more than 900 hours, and I think this is the close-up. But here you see, for example, that your conductivity of your recirculated seawater was going up to, I estimate, 2-3 times normal concentration of seawater. And the red line is mentioning the conductivity of your distillate, and it stays low. So the average value here was 7 microsiemens per centimeter, which is really good water quality when you do it in one step with MD. Another application I already mentioned was produce water. This is in the middle of Texas, in the desert. We're doing there also testing with MD. And the thing with produced water is quite challenging because it's really dirty water. You have to take out the oil, you have to take out here the iron. So that's giving you some problems on your MD body. But for the rest, it was working quite fine. And we could go up to a really high salinity. But it will also result also in really low fluxes. So you also have to make it, one, working, and two, you have to find your sweet spot to operate it at the lowest cost for your client. So, but it can also be used for this one. A totally different application where we never thought of, but we're working on this for several years now, together with the University in England and the Gates Foundation. And the goal here was to make a toilet that was not depending on water and not giving you wastewater, because wastewater is causing a lot of diseases. So it was the goal to build a really cheap, not cheap yet, but a cheap toilet that can do without water. And now they're testing this toilet in China at several, how to say that, households. So real practice. And people are going to the toilet every day. And there are also the quality aspects. And the water we are producing with MD in this application is used to flush the toilet again. So you circulate it all the time. So this is also a nice example of an application where maybe it's the future of MD lying in, but it's real wastewater application. Here we have some results. On the left side, it's the feed. The distillate is clean, and on the other side, you have concentrated brine water that will be added to the solids, and then you evaporate the water, and you have a kind of zero liquid discharge system that you have to collect every week, and it's not contaminated anymore with viruses and bacteria because you have a really high temperature of 300 degrees Celsius for this house solid waste application. I don't know much about that, but I was more involved in the liquid part of this. So yeah, you had 4 applications we are working on, facing every application is facing some problems, challenges. It's a better way to say it. But in general, you always have the trade-off between the quality aspects and on the other side, the heat versus the flux. So that's a really interesting research topic in MD, where you always face challenges in construction, but also in operating, finding the right things and optimize the system as a whole. So I hope this gives you a bit of an insight on the MD side we are working on. So maybe there are some questions.
Thank you, Bart. We have time maybe for one question.
I see people clapping their hands, but I cannot hear it. So.
Thank you. We have time for one question. Don't know if someone has a question, curiosity. No. Okay.
Maybe.
Yeah, but maybe you should come next to the computer. Sorry.
Really?
So maybe just one curiosity about the treatment of produced water you mentioned, since we know it's very important to take care about scaling there. What is your experience about it?
Yeah, one of the things we faced at that application was iron oxide. That was more depositing on the membrane, so we're not happy with that because you also have to get it out. Scaling, we always want to try to prevent that in MD because scaling is crystallization on your membrane. And often it's really, some salts are quite easy to get off, but some salts are really hard to get off. And it's always the hard ones that attach to the membrane. For instance, barium sulfate was one of the issues. So we try to stay out of that. So when it happens, we try to treat it cleaning in place with an acid. So for instance, hydrochloric acid sometimes, but most of the time citric acid. But to try to prevent it. And then sometimes it is spoken about in MD world about membrane crystallization. I still don't think it's a good idea to have crystallization on the membrane, but I think membrane distillation can have an added value to crystallizers because it's more than a control mechanism on the crystallizer. But for MD in general, I always try to prevent scaling.
So having a pre-treatment in place.
Yeah, of course. We dose, for instance, in the Caribbean, we dose anti-scalant to the circulation flow, of course. And that will help you up to a certain level of salinity, of course. So we also did a couple of years ago in the Mediterranean testing at Alicante, I think. And there we also went up to 200,000 ppm. But you're asking for trouble when you go to that region, because then you get scaling, of course. So we always try to be a bit below that. So use some anti-scalant, and then go up to an higher recovery that reverse osmosis can, because reverse osmosis can typically go to 6-7% of salt. Sometimes we can go up to 14 without really getting in big trouble with MD. But most of the scaling, what we observed at Bonaire is the scaling will not occur in the membrane, it will occur in the heat exchanger we have in the loop. So the nice thing about that is you're scaling in the heat exchanger, which can be easily cleaned compared to the MD modules.
Okay, thank you.
Sign because we measure the pressure difference over the heat exchanger, so we are warned that scaling will occur at a given moment. So,
thank you.
Thank you so much, Bart. So maybe we can move on to the next talk by Melina Rocamente from Aqualia on the exploitation contents and market opportunities on solar-driven water treatment technologies. Thank you, Melina. I think you can share your screen.
Okay. Hello.
Okay. Okay. Think you can share your screen now?
Okay.
Not yet. Okay. No. Yes. Just needs to be in presentation mode and. Okay. Perfect. Now. Thank you so much.
Okay. Perfect. Thank you for your introduction. First of all, I would like to thank you for inviting us to this activity or workshop. In particular, I would like to thank Isoyer for the invitation. Okay, as you said, I'm Melina Rocamante. I'm currently part of the Innovation and Technology Department of Aqualia, where I work as a researcher. Okay, the title of my presentation is Flexible Multivariate Demonstration Plan for Regeneration and Reuse. During the presentation, we will see some of Aqualia's technologies for solar driving wastewater treatment. Sorry, if during the presentation I lose connection, I'm sorry, because we are having a lot of problem with the internet connection today. Okay, the presentation will be divided in the following content: motivation and objectives, introduction of hub Reusa, technologies for large medium populations, technologies for small population, and illustrative video of the hub. I will start with the motivation and objectives of our work. Okay, to understand of our project, it is necessary to know the motivation behind them and the needs they meet. The water stress has become a problem affecting millions of people worldwide, including more than 100 million people in Europe. Intensification of water scarcity in Europe caused by global warming is a reality. 30% of the total European population lives under water stress situations. This problem is exacerbated in the Mediterranean countries, Spain, Italy, Cyprus, Greece. Besides, agriculture is the most important water use in the European Union. About 70% of the water is extracted for fresh water resource. Okay, the main objective of the reuse platform is to demonstrate the use of a novel, modular, and flexible solution to produce reclaimed water for agricultural irrigation. Sorry. The combination of these technologies will produce a high-quality effluent that can meet the new European regulation while addressing other contaminants, such as contaminants of emerging concern and microplastics. Also, seeking to reduce the operating cost of tertiary treatment and minimize risk to the environment and human health. Okay, the new regulation introduced a greater restriction on certain maximum values that than the existing legislation in Spain, in this case. As can be seen in the slide, the new law is of the order of 10 times more restricted for the E. coli parameters and of the order of 2 times more restricted for parameters such as turbidity and total suspended solids. Also, the regulation includes a validation monitoring of reclaimed water. In this case, 3 microbiological indicators are specified for this validation: E. coli, total coliphages, and Clostridium perfringens spores. All new technologies must be validated before the implementation. Okay, next I will talk about the reuse platform. Its name is Regeneration and Reuse of Wastewater for Agricultural Uses. In Spanish, its name is in Spanish is Regeneración y Reutilización de Aguas Residuales para Usos Agrícolas. The platform is located at the El Toyo Wastewater Treatment Plant in Almería, Spain, and operates directly after the secondary treatment of the wastewater treatment plant. It is a full-scale demonstration plant with more than 16 technologies and a surface area of 6,000 square meters. Okay, this platform has different technologies that are associated with the type of population they are aimed at. We can divide them into technologies for a large, medium population and technologies for small population. This slide shows the technologies associated with each type of population and the possible combination between them. Okay. Okay, now I will talk about the technologies associated with a large, medium population. It is possible to divide them into 3 treatment units: physicochemical treatment, filtration, biofiltration treatment, and oxidation disinfection treatment. We start with physicochemical treatments. In this case, we have 2 technologies, Clarifast and DAFast. First, Clarifast is a compact system that combines ballasted flocculation and lamellar decantation. The system allows flexible operation with variation in flow from 20 to 50 cubic meters per hour and effluent load. In this system, sand is added to improve flocculation. This increases hydraulic velocity and reduces retention time. Okay, the process consists of 3 phases: absorption, coagulation, flocculation, and decantation. In the first step, powder activated carbon is added to remove dissolved organic matter here. Then, in the coagulation chamber, polychloride is added, which leads to the formation of colloid from the dissolved matter. After that, water enters in the flocculation step here, where the polyelectrolyte is added. The action of a mixer and the addition of sand produce a large flux. These flux steadily easily. The water then enters the lamellar decanter here, where the flux are separated for the treated water, which pass through the lamella to a settling tank. Clarifast has a sludge system where flux or sludge and sand accumulate in the hopper where they are pumped to the hydrocyclones. These 2 hydrocyclones. There are centrifuges separate the sand for the sludge so that it can be reused. Okay. On the other hand, the FAST is a compact treatment system for low-density particles by flotation. The system offers high flexibility in terms of flow, again, from 20 to 50 cubic meters per hour and effluent characteristics. To improve the flocculation, air or ozone is added to increase hydraulic velocity and reduce retention time. This system has an innovative lamellar distribution system. In this case, the process consists of three phases: coagulation, flocculation, and flotation. The coagulation and flocculation stage are similar to those described for Clarifast, except that in this case, no microsand is added in the flocculation state. In the flotation stage, microbubble pumps create teeny ozone or air bubbles, which are injected into the flotation unit here, leading to the separation of the suspended solid trapped in the flux. Okay, we now turn to filtration, biofiltration treatment. We'll start to talk about the Puracer. Puracer consists of two sand filters called Sol2H2O, which is an Aqualia patent of different granulometry in series with continuous washing. This technology is designed for a treatment capacity of 10 to 12 cubic meters per hour. Some advantages of this technology is 90% less of water rejection, 90% less of air, and 50% increased solid retention and improved turbidity. It should be noted that the innovative washing system of this technology has recently been patented by Aqualia. Okay, Puravac. Puravac is a continuous wash filter using biologically activated carbon has filter media. This equipment is used in combination with ozone. The water is first ozonized and then enters the equipment. Ozonation usually results in the formation of products that are more degradable than the original compounds, which increases the efficiency of the back filters. Okay. This filter is a gravity filter made up of submerged disc. The system is based on one cylinder filter joined to a collector. Filtrated water flows into the cylinder containing thin fibers that retain the suspended solids, allow it to obtain an effective turbidity reduction. Also, this filter is designed for a treatment capacity of 10 to 12 cubic meters per hour. One of the main advantages is the simplicity of the cleaning system, backwashing by suction, with a compact design that allows a significant space saving when installed. Okay, we know that in many cases, salinity is a barrier to reuse in many cases. For that reason, in the reuse platform, we have different filtration systems such as ultrafiltration, reverse electrodialysis, and nanofiltration. Okay, let us now turn to the oxidation disinfection treatment. We have chosen two ozone generators of 200 grams per hour, working at high ozone concentration, fed by oxygen generated on site and cooled by a chiller, giving the same performance as an industrial plant. Two different application points with ozone are used to achieve the target for each water treatment line. The first to improve flotation and compare its results with the use of air is the same as the first with the use of ozone, and contact tower for tertiary treatment. of the effluent, for tertiary treatment of the effluent. The ozone that does not react in the contact tower is eliminated with an ozone destroyer. UV reactor have also been installed to complete the disinfection process. Okay. Pretreatment for or technologies for a small population. Pretreatment for a small population managed by Aqualia consists of a 3,000 square meter microalgae raceway pump bioreactor, followed by dissolved air flotation, which separates microalgae from a clarified effluent. This effluent feeds wetland, a solar photophotosynthesis and UV lit pilot plant managed by CSOL, and a zeolite nutrient recovery system managed by SETIN, partners of a Life Phoenix project. The microalgae raceway can treat up to 250 cubic meter of wastewater per day, with hydraulic retention time between 3.5 and 5 days, more or less. The reactor was designed with a compact configuration to fit in the available surface. An overflow drain ensures a constant water height of 0.3 meters. A constant flow velocity of 0.3 meters per second is maintained to help with the mixing system control, which plays an important role in the correct diffusion of light. Sorry. In terms of wetland, we have a 4 wetland consisting of phosphorus absorption filters that are stable for more than a year and provide us with adequate release of phosphorus into the soil as fertilizers. Each wetland covers an area of 50 square meters. This technology allows us to achieve complete nitrification, turbidity reduction, total suspended solid reduction of over 90%, and pathogen reduction of 2.5 log. The CSOL Research Center, a partner in the Life Phoenix project, has two types of technologies based on photophantom. On the one hand, they have a pilot plant with a raceway to carry out the solar photophantom process in continuous mode. And on the other hand, they present a laboratory scale pilot plant in which they carry out the photophantom process with UVC and UVA LED radiation. The performance of the wetland has been tested in this plant. Okay. The SETIN Research Center, also a partner in the Life Phoenix project, presents 5 zeolite nutrient recovery columns plus UV lit disinfection. In this case, using reactors with a horizontal design. Okay. There is a technology jointly managed by Aqualia and CSOL, a plant for the regeneration of urban wastewater based on a linear Fresnel solar collector. Okay. The operating scheme uses solar radiation to eliminate pathogenic microorganisms contained in the wastewater, thus obtaining water sustainable for reuse in agriculture. The Fresnel solar collector concentrates the solar radiation on a UV transparent glass tube, with the wastewater circulates, increasing its temperature. In this way, the synergistic effect between the operating temperature and the incident UV radiation achieve disinfection of the water. The novelty lies in the scale and scope of the application, as well as in the overall operating scheme, which consists of the following key elements: a heat exchangers that act as a thermal energy recovery state, using the heat from the output water of the solar concentrator, reclaimed water, to preheat the wastewater entering the system. Dosage of a chemical agent to enhance disinfection during the hours of low irradiation. Okay, and finally, we are going to watch a video in which you will be able to see the facilities of the reuse platform. First, I would like to apologize for the fact that some of the description in the video are in Spanish. Sorry.
Creo que el vídeo no tiene sonido.
¿No?
El vídeo no tiene sonido, sí.
Yo lo estoy escuchando.
Sí.
Perdona, no escuchábamos el sonido del vídeo.
Vale, pero yo sí lo tengo, o sea, yo lo tengo con sonido.
No
¿Otra vez?
Bueno, sí, sí. Después nos envías el link del vídeo y lo enseñamos. Sí.
Una musiquilla, no explica nada durante
Vale,
el sonido, ¿vale?
entonces,
Es solo música.
Vale, entonces podemos ver, sí.
Vale.
Sí.
we have a lot of technologies and a lot of option of combination. All of these technologies can be used independently or in combination. It is important point. Thank you for your attention.
Thank you so much, Melina. So we have time for 1 or 2 questions, curiosities.
I have one curiosity.
Maybe, sorry.
Hi, hello. Thank you for your presentation. It's just a curiosity regarding your Fresnel. Do you have in mind what was the supplier or the power to the Fresnel?
No.
No? Okay. But can you send us?
Yes.
Ah, do you have? Okay, this is interesting.
Yes.
Okay, thank you.
Nothing.
Thank you so much, Melina.
Thank you.
It was very interesting. So maybe we can move on to the next talk by Fabrizio Vicari from Resources on the exploitation, contents, and market opportunities on the audit technologies, brand valorization. It's here. Yeah. Thank you, Angel. I have to share. No, I have to share it. Yes.
So, good evening, everyone. Thank you for having me here, for inviting me here. And I know it is tough for this presentation now after this long meeting already, a lot of contents, a lot of information. I knew that that was going to be tough, so I reduced the amount of information in these slides a lot. At the beginning, there were 96 slides. I managed to have only 60, but zero real calculation or complicated stuff. Mostly pictures. Okay? So, I'm Fabrizio Vicari from Resources, which is a spin-off company from the University of Palermo. And what we do is trying to apply the circular economy concept to the management of brands in order to extract value in different ways. Where should I point?
Sorry, no. It's not. You have the pen there.
The manual.
Sorry.
Okay. So.
Because you have the pen drive.
Okay, no problem. First of all, we are going to see some trends and opportunities in the brand management sector, and then a couple of examples. This is the first challenge that all of us is facing nowadays, water scarcity. This is the official report of the EPCC. And these are the forecasts that we see for the standard precipitation index in the Mediterranean area. We can see how most of our regions are going to face dramatic reduction in the precipitation, meaning that we need to find an alternative way to rain in order to provide for our fresh water. And this is even more clear in other extract that we have from those studies that put the color red all over the Mediterranean area, meaning that we are going to face in a quite long time frame high or even extremely high reduction in the water availability when compared to the withdrawals that we are have because of the increase of population, but also because of the increase of standards, the hygiene, and the food requirements are going to grow while the availability is going to decrease. So, what we've been saying all the day long is sorry, the other way around, we can go for desalination. And we know that reverse osmosis is nowadays a standard in the desalination market, at least for what concerns seawater desalination. But we need also to start thinking in a sustainable way about brine disposal. So for the time being, when it is done in a proper way, brine management is not an issue. When you do have proper diffusers, you measure the concentration across a straight line from the exiting jet, and you can assess that the concentration is reduced to that percentage, you're fine. We respect the limits, there's no problem. But we know that when we are in a limited geographical situation, such as the Mediterranean or even closer basins, that is going in a way to alter the ecosystem. So we need to take into account this problem. So maybe minimal liquid discharge, zero liquid discharge could be an approach. And what we want to do is to treat the brine. First of all, trying to squeeze as maximum as we can that brine in order to harvest the most important product of that water, the seawater, which is water itself. So we cannot neglect the maximization of recovery. And then we could go for some salt extraction and minerals extraction in general, but also chemicals extraction. Here is an example of what we can do with a conventional thermal brine crystallizer, but also with evaporation ponds that we have seen before. And then we need to take care. Here it is reported the worst case scenario in which what you extract has no value because you're maybe extracting a mixture of sulfates and chlorides, which nobody wants. So you need to take care. In the best case, you can go for a fractionated separation, and that way would require you to face another challenge, which is finding a market for those minerals that you extract from desalination brines. Okay, this is a very broad and conventional scheme. You can make it more complex as much as you want, but in some way you need to have these elements. Now, there are opinions that says that you should use reverse osmosis in a certain frame of salinity, while you should go for thermal processes and brine concentration in other ranges of salinity. That brings your energy consumption in a competitive path. But there is a technology gap that can be an opportunity for the proposal of several different technologies. As we have seen, the most diffused approach in this opportunity field is the osmotic cascade. So different strategies of having a cascade of multiple units that phase the big osmotic pressure that has the desalination brine step by step. These are ranked in a TRL fashion, so we see the CCRO, which now is more known as EFRO, at the first place, because at the time of when I prepared this slide, were the most ready for the market. And now I must admit that they are all more or less close to each other, because already after 1 year, I prepared this specific slide 1 year ago, but now we had, as an example, for R, the Maven in Philippines, and that is facing a rapid progress right now. So we have several industrial pilots already running. So the concept of the osmotic cascade is very old. The first one said was Sidney Loeb. He said a lot of things. If you don't know Sidney Loeb, you shouldn't be here. But Sidney Loeb was a genius, and he invented many technologies that nowadays we are exploiting. So the first one, and this concept of the osmotic cascade was him, and what he said was, okay, if you want to go from 7%, which is more or less the desamination brine, to the saturation of sodium chloride, you need to face 276 bar osmotic pressure, if you want to do that in one step. But if you do that little by little, having a loop of recirculation of the brine for the following unit, then the single step will take you less. And you can do that with reasonable means. And this is what a couple of years later, in 2018, Gradient's done. They also managed to have a patent on something which was already known. I don't know how they really do it, but it doesn't matter. What they did was to bring this concept to the market. And this is one of the most urgent challenges that we need to face. Everything that we do needs to get the market at some point, and this is what they did. And they did it exploiting an opportunity that was there. So there was Awako, leading provider for Saudi Arabia of freshwater biodesalination, that had an installation in Jeddah that couldn't be enlarged by enlarging the seawater feed capacity. So there was this strict limitation. So the only way for them to increase the water production for an increased population, we know that these cities are seeing a very exponential growth for their people, was only to increase their growth. They didn't have any other option. So Gradient went there and said, we can do that. And they did it. They increased the capacity. The plant is actually running at full speed capacity from 3 years. And this enabled the delivery of a very relevant impact. After this collaboration, other many came for Gradient. And at the end, what happened after a couple of years is that Radiant became the first and only unicorn in the water sector. Maybe this is something that you don't know. What is it, a unicorn? It's a startup company that gets 1 billion valuation, which is a very high value. Of course, after that, everybody starts calling Gradient and say, hey, sell me something. And this is happening now. You can see on the web all the review about the performance. And this is a very successful case study that we should take care of. Another case study that I want to discuss, which is closer to our Mediterranean basin, is the Saltworks bittern case. So this is a conventional saltwork. All of us have seen this kind of installation in our countries at least once in our life. No? What happens is that water enters in the first basin, gets trapped, and then starts evaporating. This, for us, is very convenient because at the beginning it starts with natural softening. So calcium salts are crystallized in the form of carbonates and sulfates. And what happens is that while calcium at the beginning a little increase and then decreases to value close to 0, we have seen maximum 400 ppm of calcium at the end of the process. The other salts like sodium and magnesium, cations, such as sodium and magnesium, start growing very high. Sodium at some point, of course, gets saturation and stabilized, while magnesium grows further to values which in some cases exceed 50 grams per liter. The maximum that we have seen in saltworks was 100 grams per liter in special saltworks in Croatia. So that it is another opportunity. Softening for free, so they do the work of removing calcium. Very high concentration, it means that with a small volume, you can have a very high productivity. So we started thinking about a way to respond to a need of the European Union, which is a way to produce magnesium. This is the list of critical raw materials, the actual one, but it is true that also when everything started was more or less the same. There is something changes in time, but these are the minerals that we require in Europe. So you have an opportunity, there is a need. Shall we make a business? And we started creating first experimental apparatus for separating magnesium in the form of hydroxide by just mixing the things and see what happened. And the problem was, this is a movie, it's not a picture. So it should go down, but it doesn't. Because this is what happens when you mix something which contains magnesium with something which contains hydroxide. It stays there for decades. So maybe we should control supersaturation in some way. Let's try to put some sodium hydroxide there little by little in the line and see what happens if we do it very slowly. It didn't work enough, but that was already something. Then the concept evolved. First, you have already seen this picture because this work belongs to that research group. And then finally, the definitive design came with the foundation of resources. And this is the core of the patent that we have about this reactor that improves the crystallization by controlling local supersaturation of the system. She is already granted in Italy and under examination all over the world. We've been trying this reactor in many different projects. I'm just showing this, the application in the zero brine project. I'm showing this one because with this kind of control, you can think about separating the crystallization of the two divalent cations, which are magnesium and calcium, very finely. We had purity close to 98% in the first crystallization step, but good purity, but you don't need so much purity afterwards for the separation of calcium too. That is the plant that was built and shipped in the Netherlands. And this is what happened a couple of years later in the circular mine project. You have already seen these pictures. We evolved again the concept, make it modular so that you can arrange several vessels in the same speed with small modification. But the most important thing is that we finally managed to have something fast to separate. If you compare the this is a settling curve, two settling curves. The first one represents a conventional mixing with a T, where you inject the alkaline solution next to the solution containing magnesium, and you just observe what happens. That is our reactor operating with the very same solution. And you can see that this is a logarithmic scale, while you have few millimeters per hour in one case, you get 500 half of a meter per hour with our system. And then, now we can appreciate that it is actually moving down very fast. One of the ways we did it is through computational fluid dynamics study, and that is a sketch of the reactors during the design phase. You can see the vortex created by the flow and the propellers which are in the tube. But yesterday we went to the saltwater installation where we provided that reactor, and you can see now that sometimes computational fluid dynamics get close to the reality. Okay, so the reactor itself is part of many different applications. You can protect a product as the reactor, but you could also protect a process where the product is used. One of these processes is indeed for the extraction of minerals from bitters, which is the core of the circular method, which is a fully integrated scheme for the recovery of minerals from bitters. And it also entangles the possibility of combined desalination, the production of sea salt, magnesium in the form of dioxide, lithium, and other elements belonging to the list of critical raw materials. This project was a great success, coordinated by the University of Palermo. Professor Cipollino was the coordinator there. And we evolved the knowledge of all these points so far away from the beginning. But the most important, for me at least, I don't know for Professor Cipollino, but for me the most important success was the construction of the first fully integrated circular economy of brines pilot plant in the world. So this was the first one. A couple of months later, we had the Mazda project, the Maven project, another project that could claim similar success. But this was the first one, operating with real solutions. Usually, I also put a video at this point, but since the presentation was long enough, we go directly to the conclusion. Now the plant was moved next to the saltworks. Paula knows that place very well. Because the objective is to switch from the prototype of the circular mine project to a real industrial plant. We also created a new company, Maremag, whose objective is indeed to produce minerals from saltworks. The only objective of this company is to produce and sell minerals. This company is the core of another project, which is the Maremag Life project, which started in September 2024, last year, and is now trying indeed to accomplish this TRL step forward from the prototype to a proper industrial plant. And we look forward to see if after the Maremag Life, we can go to a great scale up. So the Maremag Life project, again coordinated by the University of Palermo, see as participant resources, but also important pieces of the puzzle, such as Sosol, who's the owner of the bitter of the saltworks, and CIMA. CIMA is the owner of the need. So we have put together in the same project who has the resources, who has the technology, who has the need. The need for magnesium hydroxide, because they produce flame retardants for the cable industry. So they give us a constant feedback in order to see if we are on the right path to produce what it is needed by the market. So we are switching from the big overview of Europe needs magnesium to the small view of this company needs this magnesium in this way. So the business of the company that we have created is exactly to respond to this need. But then, apart from the direct exploitation of this intellectual property, we aim also at perform some trials for indirect exploitation. So we want to see if it is exportable, this model. So in the project, we have also Hellenic Saltworks, which is the owner of many different saltworks in Greece. But one of these saltworks, the one of Kypros, is another opportunity because it is a very old, low technology level with an industrial context which makes it not prone to tourism as the rest of the country. So Hellenic Saltworks want to renew this place, make it modern, and trying to get it upgraded in order to have also the production of magnesium hydroxide there. And this is the last slide that I wanted to show you. So we have seen that my opinion is that impact of the technologies is in the market. Everything else is good to have it, but first of all, we need to have a financial. There is no a single way you can sell the mineral, you can sell the technology, you can make it producing by another people, but you need to get to the market in some way. Whenever there is a need, somebody that is a needy situation, you have an opportunity to procure this impact. We have seen that there are many challenges that are still open for the brine mining sector, and I've shown the path for facing one of those challenges that was a very long and complicated challenge for producing magnesium hydroxide. And then one of the things that we would like to show in the future is how we face the challenge of replicating something that we have seen in one place in another place with the Marmac Life project. And thank you so much.